Okay, we've got 72 in the room so far, so I think we should probably kick off the day 2 of the ABHUG 2021. My name is Scott Schwieger, and I'm hosting the WebEx sessions. And now I would like to introduce Bob Anderson and Barry Dooley, our moderators, and
Hi.
kick it off, Bob.
Thanks, Scott. Let me welcome everyone back. If there's a few new people, I know there are, welcome to you as well. We'll not spend too much time on the opening remarks, other than to say when you, if you have questions as we go forward, you'll submit those in the chat section down at the lower right-hand corner. They'll go to Scott, and then they'll get forwarded, and we'll bring them back up at the appropriate time. Let me introduce the steering committee. David Addison with thermal chemistry from New Zealand. John Blake from CleanCo in Queensland. Russell Coed, HRL Technology in Victoria. Mitchell Drew from ANST, New South Wales. Armand Durant from Genesis in New Zealand. Stuart Mann with AGL Victoria. Keith Newman with Synergy in Western Australia, and Charles Thomas with Quest Energy also in New Zealand. I'm in Florida in the US. Barry is in Southport in the UK, and Scott is in Brazil. So we're scattered all over the world today. All right, Benjamin Ho, are you, we'll unmute you and you'll get your screen up. While you're doing that, I want to thank our sponsors you see here. Barry and I run these conferences. There's the sponsors. What I was going to say on that other slide is Barry and I run other conferences, HRSG Forum in the US, European HRSG Forum in Europe, and now ABHUG. Some of you have probably attended all of those, and of course, everyone's welcome at all of them. Here are our sponsors for this meeting. We appreciate their participation. It keeps the costs down and gives you the opportunity to hear and talk with and investigate services and products of people that support our industry and in particular support this forum. So I encourage you to visit with these folks via phone, email, and so forth, and listen to their brief little presentations when they make them, and hopefully some goodness will come out of all that. So it's Mettler Toledo, HRST, Energy Plant Solutions, Anodamine, Nalco Water, Water Treatment Services, HRL, Duff McIntosh, which is a partner of Century, RTR, and SWAN Analytical. Here's our agenda. I'm not going to read through it. You should have it. We're going to have to stay pretty prompt with the timing so we can get through it all. It's going to be like 1 a.m. or after for Barry when we're done. So we don't want him falling out on us part way. So we have to keep moving right along. All right. So our first presentation is Benjamin Ho and Michael Jantz with INPEX. So you want to say something, Ben, and so we can just make sure your audio is working. Hello, Ben.
Hello, sorry, I'm having some sharing. I think I'm sharing the wrong item. No, there we go. Good morning, all.
Yeah, can you run your volume up just a little bit? If you can.
So the microphone. All I can do, I think, is sit really close to my laptop. That'll have to do. Is that okay?
It's a little weak, but I guess
It's a bit quiet.
tell you what, let me get my this week has caught me. I'm normally based in Perth, but today I'm in Darwin.
Maybe.
Can you hear me?
Is
that better?
Maybe, Scott, you can tell him how to do it on the mute, how to turn it up.
I think he's good right now. Go for it, Ben.
Is that good?
Okay.
Excellent. Okay, well, thanks for that. Good morning, good afternoon, good evening, everyone. So before I begin, I'd like to confess to the cardinal sin of putting way too much detail on my slides. So I'll have to gloss over certain topics and we can come back to them during Q&A or during the discussion session. Unfortunately, Michael hasn't joined me. I don't think he's actually arrived on site yet, but I'll have to keep going with Adam. So some recognition of our joint venture partners and our standard disclaimer. I'll move this out of the way. Sorry. Okay, so today we'll just introduce the ICFIS project to the ABHUG audience, looking at the onshore combined cycle power plant, or CCPP. We'll go through its design and key equipment, the HRSG design, operating philosophy, some plant history, which neatly takes us into discussion of some of the challenges we have or are still facing today. Okay, so in a nutshell, the ICFIS project is INPEX's first owner-operated project with a whole bunch of subsea infrastructure, 2 massive offshore facilities, an 890-kilometer subsea pipeline to the LNG plant near Darwin. This is an aerial photo of what most of the onshore LNG plant looks like. It is what's called a 2-train LNG facility, so 2 processing units that take feed gas and turn it into products. Headline numbers, it can produce a lot of LNG, a lot of LPG, and a heavier hydrocarbon liquid that is called condensate. Despite all the challenges we've had since FID was reached in 2012, since starting up production, we have been producing cargoes at a rate that puts us in the upper echelon of similarly sized plants globally. The power station shown in this yellow box, of course, is one of many key utilities on the plant. Within Australia, this LNG plant is the only one I know of that has a combined cycle power plant rather than a bank of just gas turbines. And from a design point of view, that was probably to achieve more energy and emissions efficient power production. And originally there was an intent to use of excess isopentane coming in from offshore. This gives you a bird's eye view of some of the key equipment. So there are 5 40-megawatt gas turbines, each with an HRSG, a set of common piping headers of steam, condensate, and water, which I'm told is a very rare design these days, but there are reasons why we have this set up, which we'll get to shortly. 3 100-megawatt steam turbines, and each with an air-cooled condenser. And that adds another degree of uniqueness, as there are only 6 Australian power plants with air-cooled condensers that I know of. The metallurgy is all ferrous, so we use extensive amounts of carbon steel, P91, P11, P22. That steam header has a sliding pressure, traditional AVTO to go with that all ferrous metallurgy, using ammoniated water and provision for triiodine phosphate at the drums. If you sum the total outputs of all the equipment, you get to a nameplate of 500 megawatts, which is more than double, theoretically, what we need to run both LNG trains, and is close to the total capacity of the entire state. But there are reasons for this excess output, which we'll get to shortly. These are some drawings of HRSGs. They're very simple in being single pressure drum units with no reheating. I don't know what the technical word is, but the economizers have that down and up flow. Some other features are some economizer recirculation pumps to mitigate this dew point corrosion, duct burners, an interstager temperator, high-level design numbers, 12 megapascal design pressure that we never operate that high, and an outlet steam temperature of about 534 degrees Celsius. The plant was designed as a pure power island, so there's no grid connection. And it was designed first and foremost to provide a reliable supply of power to the LNG facility over maximizing efficiency. Because of that, it was designed with a large amount of spinning reserve. The total demand is shared between all the operating units. If an HRSG were to trip, the gas turbine will continue in simple cycle. The number of total generators is 8, and we have what's called N+2 sparing, which means that you can still have, you can lose 2 turbines of any type and still continue producing at close to maximum production. And there are a variety of combinations that can reach either N+1 or N+2. So in practice, we have been forced to live with N-1 due to trips and other issues. And that being able to achieve that is partly due to conservatism, upwards conservatism in the power demand and upwards conservatism in the, or rather the downwards conservatism in how much power we can get out of each unit. Going into some plant history and without going into too much sordid detail, there were some very well publicized contractual issues during construction. And this shows up to a degree in the gaps between the first and the last gas turbines to be started up, the gap between the last gas turbine and the first steam generators. And if you're very eagle-eyed, you might notice that this date of the first HRSG startup is almost a year after we started producing our first few LNG cargoes. But anyway, they're all online and they've now been operating for about 2.5 years. Prior to getting to this point, the operations team that I'm in did well before commissioning, an RBI assessment across all facilities, including the power plant. One of the RBI team members was a very good power plant chemist who did a pre-commissioning review of our steam chemistry, looking at the analyzers, listing out all the things we should be doing. That work then fed into a very EPRI-centric chemical treatment guideline, which was reviewed by everyone and issued for use. And then prior to introducing steam to our turbines, we had an independent site chemist come to our site, give his opinion and make some very important recommendations. To this day and age, we are still refining our RBI programs using expert help, as well as live data from parts of plant to understand how our plant runs. There is significant effort in trying to improve reliability of the plant. So there's a formal reliability improvement program in place across different disciplines and themes. And we launch RCAs upon almost every event that happens. And there have been many events. We are still very much in the infant mortality part of the bathtub curve. I should probably move this arrow a little bit to the left, if anything. And this here is just a laundry list of all the issues we had or still have. But for the sake of brevity, I'll only focus on the sort of top few. So for my team, probably the single biggest threat to integrity is the steam and water analyzer, or rather the steam cycle chemistry. So we had the best laid plans prior to startup with an RBI and all these reviews and guidelines in place. However, when we had those significant contractual issues, there was a lot of equipment apart from the turbines that was poorly preserved and left idle for about 6 months. So by the time the replacement contractor came in, the rush to finish construction has left us with a number of legacy issues which we're still grappling with. So, for example, every single steam and water system circuit, be it just closed cooling water or the steam system, has been handed over with one or more parameters out of spec or just plain bad condition. There was chemical cleaning done, and the documents all clearly stated it was done. However, it was done at ambient temperature rather than heated, so that wouldn't have done too much. And early on, either because of or construction debris left behind, we found very high metals. I've seen analyzer readings of DO at 400 ppb. Silica's been high, sodium's been high. And compounding all this is that our SWAS is very unique in being a very low shelter, high maintenance design. We have 2 deaerators, the first of which was operating but poorly. The second one was unavailable due to some broken valve parts not being available. And as a result, our sole plant chemist has been heavily reliant on portable DO measurements and grab samples. Since those early days, we have been improving. Fortunately, the operators have been dosing a lot of ammonia to keep the pH up. They weren't consciously targeting 9.8 to 10, but they were inadvertently getting pretty close to that. Now we have fixed that second deaerator, and it's actually performing so well that it's telling us that something's wrong in deaerator A. A decision we're grappling with now is to replace our our low shelter, high maintenance SWAS with a proper SWAN containerized unit. And from what I'm hearing, that's very much a go. It'll just take some time. And we've recently had the first of what will hopefully be a periodic EPRI cycle chemistry benchmarking study. And if your plant isn't doing this already, I highly recommend it. In our first attempt, we scored an average sort of ranking of 18, which isn't too bad. But we know we need to do better. We know what we need to do better, and it starts with the SWAS. We've been given a fairly clear roadmap. We just need to do it. On the inspection side, fortunately, from what we've seen so far on the HRSG, we haven't seen any direct evidence, either through UT or visual, of FAC on any components yet. But on the solar air-cooled condenser we have looked at, we are definitely seeing indications of, well, if it's FAC or erosion, one of the two. Penetrations are looking great, and offline there's a lot of residual water left behind and a lot of flash rusting. Turning now to our temperators, I won't read this table out, but what I will say is that we have a lot of the temperators on our site, 31 units all up, across 4 different vendors, 9 different models. The pipe sizes are on range from 6-inch to 36-inch. They are primarily the spring-loaded variable area type, but we have a half dozen of these surface absorption TCP heaters, which I'm not sure are commonly used in the power sector, so I appreciate some comment on that and the sheer number of different types and makes and models we have. Many of them are standalone, but many are integrated with pressure reducing valves. Many are lined, but a good half dozen are not lined. And the spec sheet clearly says a liner is not required, though if you look at the design conditions, it's questionable as to the logic they may have used. This shows schematically where all the temperators are. You can see that single interstager temperator on the HRSGs, but by and far, the vast majority are concentrated in the steam turbine and ACC area. Right, so we've been confronted by finding at least one cracked temperature nozzle in all 5 of our HRSGs during their first inspections, which was around about 15 to 18 months from startup. And there's a lot of work. I know I've heard along the grapevine that there's a lot of work that goes into temperators. But is this normal? Should we expect a minimum of 2 years from a good temperator, or 4 years, or perhaps more? Typically, the external cracking shows up through mag particle as cracking through all at the flats. Though once or twice we occasionally see these heavily scaled and dirty-looking nozzles, and if you look on the inside of it, you have this metallic gray appearance, which to us is very indicative that this hasn't been firing water, compared with the vast majority of nozzles which have that classic AVTO red color. When we first asked the vendor about it, to them this was a novel failure mechanism that they'd never seen before, though fortunately we hadn't seen any pipe or liner damage as of yet. Internally, this is what many of the cracked nozzles look like. It appears that cracking has started at one or more of the ligaments. The stresses have then allowed a crack to initiate and propagate in the next ligament. And before you know it, you're at the wall and making your way through the wall. We've now had 2 different metallurgists section and mount cracked nozzles, and they both agree that the cracking morphology takes the form of stress corrosion cracking rather than, say, a fatigue mechanism. And again, there's a lot more to a temperator than just metallurgy, and we're working on the process side as well, but our findings we thought were pretty compelling. So the vendor has specified an 11% chromium martensitic steel, in some ways not too dissimilar from P91, with a surface hardening treatment to improve the galling wear resistance. And they targeted a 45 to 48 Rockwell C range, which is about 450 to 480 Vickers. That might have been reasonable for those 2 characteristics. However, it is quite well known among metallurgists and in some fairly important books that these sorts of materials, at these sorts of hardnesses, are acutely susceptible to stress corrosion cracking, and theoretically in moist air. And we've gone hardness tested on the bench and portable hardness tested, probably 15 nozzles now, some brand new, some cracked, some used but not cracked. And many of them are out of spec, up to 600 Vickers, with many above 500 Vickers. There was that one very soft nozzle, that's a special case. And when we contacted the US branch of this vendor, they, shortly after we mentioned it, they reported that another US HRSG had reported a very similar issue that same week. What's interesting there is that their manufacturing date was very similar to ours, so maybe there was a batch issue there. In any case, for us, the root cause is most likely selection of a cracking susceptible material exacerbated by poor heatment control. The last point I'll make on this slide is around this oxide. So the very soft and seized nozzle had a very thick oxide on it and had to be hammered out of the stem had to be hammered out of the nozzle. And when compared with the stem of a cracked but still moving nozzle, a very thin oxide. It's the relative oxide thicknesses and the absolute oxide thicknesses for about 33 odd micron are very, very consistent with a previous ABHUG presentation back in 2013. So moving forward, we want to upgrade our nozzles to the Inconel 718 type with spring shield. And big shout out to this forum and for having this material, because without this presentation, I would have been stuck. This was instrumental to driving the conversation with the vendor to get us to where we are now. We intend to enforce traceability both externally with the vendor and making sure that they supply all the documentation that demonstrates that what they supply us actually meets their own internal specifications. And internally, we want to make sure that we know which nozzle, which serial number, with which batch ended up in which HRSG and which o'clock position. So we're going to start engraving our nozzles and our nozzle holders. We're looking at building an on-site in-house function testing rig and possibly some more portable harness testing on both used and new nozzles to see what happens over time. We'll be inspecting all our other temperators and replacing their nozzles as required. And we'll also be looking at process data reviews to see if there are any performance issues or overspray, leakage, or any other sort of adverse phenomenon occurring. Okay. A hot topic for us has been piping bellows. So these are the flexible joints used to seal in flue gas where there is a pipe running through a casing. On one of our HRSGs earlier this year, we saw a steam and water leak coming from one of the economizer blowdown pipes. And when it was delagged and drained, what we saw was a circumferential crack in the fillet weld between the carbon steel bellows end plate and the carbon steel pipe. This is kind of schematically shown at this tiny little black thing there. When we cut this section out for lab analysis, we were shocked to see a longitudinal crack in the pipe just above it. Now, all of our piping is expected to be seamless, so immediately set off alarm bells as to whether or not we had some rogue material on site. Fortunately, the metallurgical analysis showed that it was not seamless, but what it also revealed was that in addition to the circumferential cracking along the fillet weld, transverse branch cracks had initiated and propagated into the plate, but also several of them had propagated into the pipe. And you can see that there are several examples of that. They haven't made it all the way through, but there's one there, and of course there's this one here. A cross-section of part of the fillet weld showed that 1, there was a very large root gap. 2, there's a very poor weld root profile. 3, there's a crack going through it. And 4, that there probably wasn't enough fillet material there for the stresses that this pipe was under, and that's what's led to the failure. Another set of bellows we're closely monitoring are some on the high-pressure steam pipe. Now, these have a very different design where a P22 collar has been welded to the piano pipe, post-weld heat treated, and then the bellows has been welded to that collar as to avoid post-weld heat treatment of the bellows. The original NDT location was meant to be this T to butt weld just there, which is shown just here. But the cracks are so large that the NDT takes all this immediately. On the worst T in this example, 36% of the fillet weld circumference has cracked. And while everyone we've spoken to so far thinks it highly unlikely that the cracking will propagate into the collar and then into the pressure envelope, we appreciate some feedback. We think that what will happen is crack will go all the way around. You might have a little bit of flue gas coming out, but again, we appreciate some feedback there. Flange joints are becoming a bit of an issue. I'm not the expert on all of these, but we have at least 2-3 different types that I know of that have leaks. Each of the HRSGs has a blind point flange like this that is used to isolate the HRSG from the main steam header for inspections and maintenance work. It was known during the project that many of them were on the margin of acceptability when it comes to seal face condition. However, earlier this year, a couple have started to have steam leaks, and when the joint was taken apart, they found mechanical damage and pitching on the sealing faces. What would have made this, or what did make this a much more complex repair job than it would have been otherwise, was that these joints were not designed for maintainability. There simply isn't enough room to fit flange machining equipment on both flanges. So we end up having to cut off one or more of them, fabricate a DN350 drop-in spool, and relocate some of the narrow bore piping around it. So this is your before situation, this is your after situation. And we're rolling through each HRSG outage to doing these modifications. Okay. The last slide today, that's another piping failure that we've had. So each HRSG main steam outlet pipe has a outlet to which is attached a 100 DN pipe. This runs up to a control valve and to a silencer, and we call this the sky vent. When this crack occurred, there was a lot of debate internally as to whether we should do a localized temporary repair or a full circumferential cutout and a proper repair, permanent repair, if you will say. Looking at the pipe in the field, it's pretty obvious that there's a fairly long run of inadequately supported pipe above it. And when that silencer was operating, when the control valve was open, it was known that this was shaking a lot. So it wasn't surprising, and it was confirmed in the lab that it was a fatigue failure. However, two things jump out at us with that fatigue failure. One is that the root run of the weld was wide, rough, and heavily oxidized, which suggested a lack of inadequate shield gas. And metallurgical analysis showed that a non-compliant weld consumable had been used at the root run, closer in composition to carbon steel than to P91. Now, we have to think about what we're going to do next, as this is not something you can inspect for using NDT. And there could be some more rogue welds out there we just don't know about. At this current HRSG outage, we are going to cut out the next one of these in sequence and see if that also has an issue. It's not a large sample set, but hopefully it gives some good indications. So that's all. I hope you found some good takeaways there. I thank you all for your attention and welcome your questions and feedback. Thank you.
Thank you very much, Ben. Barry, do we have any questions for Ben?
I don't see any questions, but I have a comment for Ben, Benjamin. It's very nice to see LNG facilities. As you probably know, I've done the largest LNG facilities assessments in the world, and it's remarkable how common the facilities are that you mentioned are in those, single HRSGs, ACC, etc. And so I also wanted to say that I hope you don't get too much confidence out of the benchmark score that you raised. You probably know that I developed that many years ago, and we have a database of over 300 units. But the way that we look at benchmarking, Ben, is that it's reactive. It's what's happened in the past. And what I want to do is encourage you to look at repeat cycle chemistry situations, which I mentioned yesterday. There's a direct link between those, and they tell you what's going to happen in the future. And so it's very important that you can use both of them to be able to provide some security that your plant is okay for the future. So just a couple of comments for you. Nice presentation.
Yeah, I would say you've, I think for the amount of time you've been operating, you've described more problems than I've ever heard anyone else be dealing with, and you've done a nice job of following up on them. So good work.
Thank you.
Hopefully things will slow down for you a little bit here for long. Okay, we don't seem to have any questions now. If any come up, we'll include them in the session later and get back. Jerry Visser, are you with us? If so, we'll get you unmuted and make you the presenter.
I am indeed. The share button. Okay, there it's now. Can you see my screen?
Not yet. Oh, something's happening. We got it now. Perfect.
Excellent.
Well,
Good
introduce
morning.
yourself and
Yep.
have at it.
Good morning, everybody. My name is Jerry Visser. I work for ALS Industrial in Queensland, and I'm the engineering manager looking after a group of engineers and metallurgists working in the power station, gas and mining space. So I'm going to talk about the Calide B1 tube failure that we did have a look at this year. And I would like to acknowledge the following people that worked on this job. It was Bob Panchel and Mike Henry on the metallurgical side, Aaron Avalos on the fraction mechanics assessment side, Charles on the vortex shedding frequency estimates, and Mohammed Fahad on finite element analysis. I also would like to acknowledge CS Energy, who participated in the RCA, obviously from their side. Chris Ross, asset engineer looking after pressure parts, Michael McCallum, asset engineer combustion, as well as Ian Rawlings, the boiler engineering manager for CS Energy. So just a quick overview on the Calide B boilers. It is a Babcock Hitachi Kirei boiler design from Japan. It's a Carolina style unit, lateral circulation unit, with a split backpass. So if we look at the boiler use, the furnace here, furnace, superheaters and HC reheaters, we've got a reheater pass as well as a superheater pass. The boiler main damage mechanisms is largely fly ash erosion, supernova erosion, and water wall quench cracking. But then this particular failure popped up a couple of times for them as well. Steam conditions is 541 for both the main steam and reed, and it's a 350 megawatt unit. So the tube failure happened during this year, and it first started with a pressure excursion and drum level deviation, followed by a boiler and turbine trip. Walk down confirmed the tube leak around level 5 of the boiler. And if you look at where the tube leak occurred, you will see it's just above the nose, and that's the furnace rear wall. The furnace rear wall forms a nose, and then some of the tubes run through from the rear wall. That becomes sling tubes going up through to a header, which is supported into the penthouse. So the boiler rear wall has obviously got buckstays, burners, wind boxes and structures attached to it, and all of that load is basically running through the sling tubes into the penthouse. So the failure occurred just above the nose. If you look at what the configuration looked like, you'll see that is the tube from the nose going up, and here is the load from the rear wall tying into that sling tube. You'll see the bracket is welded on both sides. It's a double bracket, and that transfers the load into the tube. Here you can see the tube going up. So just a history of similar incidents. A complete tube failure at the guts connection occurred on B1 in 2015. So if you look at the failure this year, again, we had a tube failure on B2 that had a complete failure, so the complete rupture of the tube. And also on B1 in 2020, we had a crack with a leak before rupture. If you look at the failure, just what it looks like, you can see here's the two brackets coming up from below the nose, and it basically completely ruptured top tube. So that was completely separated. So there was no leak. It was just a complete failure. And there you can see the sling tube lying there in the boiler. And there is the stub that's remaining. So that's the little piece that comes through the nose. And there's those two brackets. So it just literally broke off above that two brackets. So I'm first going to talk about just the metallurgical analysis that was done. So the test performed was a typical process we normally follow. It's a visual examination, hardness testing, fractography examination, looking at the fracture surfaces, chemical analysis, and metallographic analysis. Here you can see the design data for the tube. It's sitting at around 20 MPa, 418 degrees C, 63.5 OD tube with a wall thickness of about 7 mil, and a design load on that sling tube of about 6.8 ton per tube in accordance with the OEM, and the steel is a steel 440. You can see here is the filed surface of the tube, just above the two brackets. You'll see this is the first area which cracked from the toe of that bracket into the tube, nearly through wall, and then we also had the other side which didn't grow so deep, but before it leaked, the rest of the section failed, and it's quite a large section that has failed. Here's a little bit more closer look at that tube failure. That's the first bracket. So you'll see here that the crack length was about 5.4 and through thickness is 5.5. Now the tube is supposed to be 7 mil, so there was some material loss on this side. You can also see ratchet marks from the fatigue side, and the fatigue crack grew from this area in almost all the way through. This is the other side. There you can see the ratchet marks a little bit clearer, and also didn't grow all the way through. And this was at about 3.88 before the tube let go. You can also see here what the weld geometry looks like. So the bracket is basically unprepped, just welded on both sides, and there's no weld at the top. That's just some of the hardness results. So everything checked out from a metallurgical perspective and from the materials. No issues on the hardness. This is the tube, weld, and bracket. So that was all good. If you look a little bit closer to the surface just above the weld, there was also a lot of secondary cracks. So the cracking actually didn't start from the weld itself or from the bracket, but it was just above that location. And you can see here, that's little red section here. If you zoom in there, you can see this secondary cracks that's developed there, quite sharp ends, and that was on both sides of the brackets. A lot of secondary cracks that developed in that area as well. So the big question was for everybody is why did it rupture? So initially it was thought that there was an overload event that happened in conjunction with this failure. So we had to first determine was it a ductile failure of that final fracture that occurred. And when we looked at the fracture surfaces, so this is the area where it fatigued and fatigue crack grew, and then the last portion sort of just sheared off. So if we look at the fracture surface above and below, you get these dimples, and the orientation of these dimples, if you look at the ASM fracture manual, gives you an idea of what happened and which direction the final overload was. So that all confirmed that there was a definite tensile overload that occurred on the last section. We also did a test in our lab where we notched a bar, pulled it, the notch bar, and looked at the fracture surfaces, which were very similar. So just in conclusion, on the metallurgical side, the correct grade and composition of hardness and microstructure of the tube was present. The minimum wall thickness of 5.3 instead of 7 millimeters at the failure location played a big role. Fatigue cracking evident on both gusset locations. The gussets themselves didn't crack, however. Cracking had extended almost through wall, but the tube didn't leak before failure. And cracking propagated from high cycle fatigue. The final rupture was due to ductile overload of the tube and most likely due to high tensile loading on the tube. So that was a big question. Was there something that happened that overloaded the tube? So the next step we did is we also did a fracture assessment to see if it is plausible that the tube failed under design load conditions with that crack geometry. So we used the BS7910 approach, constructed a failure assessment diagram with a failure assessment curve. We calculated the toughness ratio and plastic collapse ratio on the Y and X-axis respectively. And we used one defect, the largest one, because the cracks, according to the crack interaction rules, were not interacting. So we based the assessment on the larger of the two defects. And we classed the defect external flaw on the cylinder. And the primary loading considered was pressure and rear wall load. And we used the FEI model to get that loading from the bracket to do this assessment, which we'll talk about a little bit later. The effects of secondary loading was not considered. And we used the linearized membrane and bending stress components in the crack opening direction for the fracture assessment. So just the design, just a conclusion from the fracture mechanics assessment is that the loading with the defects present is sufficient to cause plastic collapse. So if you look at the toughness ratio versus the plastic collapse ratio, allowable versus actual, then you'll see that we've got a plastic collapse ratio of 1.32, which tells us that for the defect that we've assessed, that a plastic collapse is plausible. So that sort of gave us confidence that there's not something potentially else that's caused it in terms of overload, but that with the defects there, and because the tube is highly loaded, that those defects could be sufficient to rupture that tube completely. We also had a look at vortex shedding frequency. So we looked at the length of that sling tube versus the design gas flow across that tube and calculated the vortex shedding frequency. It's around about 30 hertz for a Strickland number of 0.2. So obviously there is a range there. So we did calculate a range, but for 0.2, it's 30 hertz. And then CS Energy also, during outages, they test their tubes for natural frequency to check if the tubes are actually carrying load. So they put an accelerometer on there and then they do a bump test and then they see what the frequency is. So the fundamental frequencies that they've measured on site is between 32 and 41 hertz. So we can see that, it is pretty close. So and they've also, during operations through a site access door, taken some video imaging of the tubes and clearly seeing that tubes can get excited. So at 32 hertz, if the tube had to be excited enough to cause damaging stress cycles, those stress cycles will ramp up very quickly because it is at a high frequency, and if it's significantly excited, will fail pretty rapidly. So that's what we suspect happened. There was a condition that occurred where these oscillations that the tube sees was sufficient to cause damage over quite a short period of time. The OEM also confirmed that anti-vibration bars are sometimes required due to gas flow excitation and would be recommended for the Calite design. So we also then did a finite element analysis for two purposes. One, to kind of get an understanding of how the loading transfers into that bracket. And secondly, to look at different designs. Like the Toorong power station is very similar to the Calite power station. and then also see if we can get a design that works, or is a little bit better. So there's 3 designs that we looked at. The original design, which is a 12mm gusset, just welds on the side, no weld on the top. Then we looked at Tarong. It had a shorter gusset with a 14mm thickness, and it was blended in. And then we looked at a modified design to see what we can do with the existing geometry on site to see if we can sort of improve that situation. That's a comparison between Callide and Tarong. You can see Callide, the bracket runs up quite high. It's got a very abrupt stop at the top, and the welds are just on the side. So the load transfers through this bracket into the tube, and if you can visualize some flow, it needs to flow into the tube. So what we're seeing is that that tip of the bracket is actually not working at all. So the stress flows into the bracket, but where it runs through that corner is where the stress is concentrating. Tarong design, slightly different, which is strange. It's an older boiler, so you would have expected that the design would be improved from Tarong to Callide, but in Tarong's case, the bracket stopped almost on the bend, and you can see here at the top of the bracket they actually filled in that little abrupt change. Sorry, just that little abrupt change to blend that weld in. And I've been on site looking at that specific geometry, and it looks, pretty blended in there. You almost can't see a notch. So that's a big finish, a big difference in the finish. And Tarong has not experienced a failure like this. So that's typically what the 2 different designs look like. So that's very, very sharp, abrupt end, where the Tarong one is more blended in. If you look at the stress results, so we got the same, where you saw that fatigue crack develop and moving in. We got that same response just above the toe above the bracket. So not on the bracket, but just above it, and similarly for the wrong side as well. So you can see the difference in thickness, as well as the difference in stress response. Here is just a comparison of the stresses for the 3 designs. You've got the Callide, Tarong, and modified Callide design, and you got the allowables for plastic collapse against membrane, and then plastic collapse against membrane plus bending, and then local failure for peak stresses. But the interesting thing is that if you look at the Callide versus Tarong design, is that the actual membrane stresses on the Tarong side is actually higher, and the membrane plus bending as well. And that's probably because that bracket ties into the bend itself and doesn't run past the bend. But the big difference was in the peak stresses. So the peak stresses was quite significantly different because that weld is blended in, and this one has got that abrupt stop. So we basically cut back that bracket and put a weld on top of it and blended it out to drop the peak stress. And that's pretty much what we could do with the geometry on the plant. So from the FEA side, the stress is close to the maximum allowable, even for a defect-free structure. So that means when they designed the sling tube, just from a pressure perspective even, we did the code calcs as well, they had that very, very highly loaded. So that's not even considering the bracket geometry. Then when we put the bracket geometry in, the peak stresses at the toe, where the bracket transferred the load into the tube, was very high and concentrates at the weld toe. And then obviously the smooth transition there in that area would help. And the cyclic stresses in that area will cause fatigue to occur at that locations, which we've seen on site as well. Most of the designs would be resilient against pressure cycles from a fatigue perspective, but when you look at high cycle fatigue, that's probably where the issue lies. So just in summary, The failure was caused by two different failure mechanisms. The one was the initial fatigue, cracking, and growth, and then the tensile overload with the reduced cross-sectional area. The nominated root causes of the event were tube vibration resulting in fatigue cracking at the gusset tube connection, high stress concentration at the gusset to tube interface, and highly stressed screen tubes at normal boiler loads and conditions too, which doesn't have a big design margin. Contributory causes are reduced tube wall thickness at that connection due to fly ash and soup blowing erosion, low tube vibration resistance because of the length of the tube. Vortex shedding frequency is in the same range, so you could get conditions where they match up. And also, what was interesting, two of the failures where we had that rapid sort of failure occurred with a stuck soup blower in the furnace. So we also suspect that that soup blower, and it's stuck at that location, has an impact on the vortex shedding frequency and possibly excites that tube. So that's in summary. It's an interesting one. So if there's any questions, please feel free to ask.
Jerry, very nice. Barry, we've got a few minutes for questions.
Yeah, there's one here from Gree. I'll read it out. It's just a short one. Jerry, he says he might have missed it, but what were the materials for the gusset and the tube made of, please?
It was steel 440, so it's a carbon manganese steel.
So just normal water wall material.
That's it.
Well, yeah, okay. And I don't see an. Let's see if there's another one here. No, the other ones are for Ben, so we'll have a question. So Jerry, there wasn't any detailed metallography, but maybe you can tell us. It would be a little surprising if there wasn't any cracking from the inside with such levels of stress or something like corrosion fatigue. I couldn't see anything.
No, all of the cracking result was propagating externally. Yeah. From the toe of the welds, and yes. All of the secondary cracking, so that whole area above that weld was full of secondary micro cracks. So it was basically fatigue at that peak stress location. The rest, there was not any evidence of any cracking from the inside.
Okay, that's good. Quite often we see it on both sides, with one being predominant. But thank you. I don't see. Are there any other, Bob? I don't see any other for Jerry.
No, we've got about five 6 minutes ahead of schedule. If you want to handle the ones for Ben, or we can move on and get those later.
Yeah, we can do the ones for Ben because we're into the question time now. But maybe somebody else has a question. Okay, so should we do the ones for Ben if he's?
Yeah, why don't we pick those two while we have this 5 minutes before we actually hit the question period.
So Ben, there's a question from Nathan Leonard, and he says, "What challenges did you experience specifically with your SWAN configuration?"
Thanks, Nathan. I will point out a certain person by the name of Dave Addison in the crowd who will know far more intimately what my problems are.
Ben, you faded out again, Ben, volume wise.
Okay, is that better?
Yeah.
Okay, so Mr. David Addison in the crowd will know my issues better than I will. So a bit of background, I'm the materials corrosion inspection engineer. So I'm not a chemist. I have training in chemistry, and I'm heavily reliant on good chemistry, but I'm not ultimately the one looking at it every day. But what I can say is that the SWAN is low shelter. So unlike a proper containerized unit, ambient temperature fluctuations will affect the system. It was designed with poor access in mind. Some equipment you have to power down to do any maintenance on it. Some equipment you have to power down and disassemble some sort of cover in the front to be able to access it. There's a cationic. One of the case instruments has a resin which had to be replaced rather, at a fairly high frequency, and our site isn't just resourced to do that all the time. So the results, you couldn't trust the results because the instruments weren't being calibrated, maintained.
Very, Ben, it's very difficult to hear you. Maybe you can just turn your sound up like you did before. Thank you for that answer. There's a question from Lester Stanley. If he would like to read, verbalize it, or I can read it out. Lester, are you there?
Can you hear me okay?
Yep.
Yeah, more just comments for Ben. I'm learning that attemperator spray nozzles are really hard to visually inspect to understand if they have good spray performance. So what I think the trend is going towards is spray testing, where you literally pull the nozzles out and put them in on a bench and pass water through them with some sort of test setup. And some vendors are offering that, and look at the spray pattern. It could just be spraying out into the parking lot. And that's maybe the only real way to understand if those nozzles are giving you good spray patterns. And if you don't have good spray patterns, then that puts emphasis on having a liner in the pipe. So I think a lot of attemperator vendors assume they're going to have good longevity on their spray nozzles, so they don't put a liner in. But really the opposite's true, where those spray nozzles they don't perform as well as they should. You get rust and debris in the water supply lines, gets past the strainers, maybe don't have strainers, and all that contributes to bad sprays. So then bad sprays cause damage downstream. So I just want to make that comment. And then I have some more comments on stainless steel bellows beneath HRSGs, if you want me to keep going, Barry.
Yeah, yeah.
Go
Yeah,
ahead.
why not?
Go ahead, Lester.
So bellows underneath the back end of the HRSG are notorious for collecting condensate and inside the bellows when you're running. So they all should have drain holes on them. And then those drain holes can help get the fluid out of the condensate out of the bellows, hopefully as fast as it forms. Then you got to be careful where that condensate goes. You don't want it draining into the insulation lagging right underneath the stainless steel bellows, because then you can get corrosion under insulation damage. And then that moisture, sometimes insulation has chlorides in it, and that can aggravate the stress corrosion cracking issue with the stainless steel in the bellows or elsewhere. So you kind of got to be careful of that. So I think another trend that I hope people do is to invert the rear bellows. So instead of hanging down underneath the floor casing of the HRSG, they protrude up into the lower crawl space if you have space, and then that eliminates that low spot. It keeps the bellows warm, doesn't collect condensate. And I've got some pictures I took this spring at a site, and it really looks nice if you have space. I don't know if I should share screen or not, but I've got a.
We only have 1 minute, Lester.
No worries.
You're now into your vendor presentation.
Okay.
I think if I can.
So Bob,
That's the screen I suggest you share.
Right. No worries.
Bob, there's two quick ones here from Kevin Cowley at Pelican Point
Yep.
for Jerry. And the first one is how many years difference is there between the two power stations? Between Callide and Tyrone?
Callide is the oldest unit's probably 1981, and Tyrone is 1981, and Callide B1 is 1987. So Tyrone is older than Callide.
Yeah, and the second, he asked who did the FEA on the design of Callide? Was that done by the manufacturer, Jerry?
No, that was done by us.
By ILS, okay. And okay, so Bob, that's I think okay for you to move on.
Okay, Lester, you want to share your screen and share some HRST stuff with us?
Yes, let me
I'll point out that while we're waiting, that HRST is one of our routine sponsors for the forum, and we appreciate that.
Let's see if I can do this. All right, can you see full screen mode or presentation
No,
mode?
yeah,
Full screen?
no. See,
All right, maybe I can figure this out. Hold on. Share. How about that?
see nothing.
It's just loading, Lester. There it
Oh,
is.
there you got it. All
All
right.
right. There we go. Good. Okay. So thank you. So yeah, this is our 10-minute talk about what we can do. HRST, our motto is inspect, analyze, solve. So we do a lot of inspection work. Then we hopefully, if we find problems, we have the capability to analyze and solve them. We work with a lot of other experts to join with us to get a lot of things solved. So ALS has helped us on a bunch of projects in the US and in Australia in the last few years. So I just want to give a shout out to them. So is David Addison in thermal chemistry. So we like to reach out to others where we don't have direct in-house expertise. We've got, let's see, six or seven locations in the USA where we have offices. And then we also have an office in Vietnam. And our engineer Hui from Vietnam is online tonight with us. And we did a lot of promotion into Southeast Asia this last couple of weeks, hoping to gather or attract some other users from Southeast Asia. So maybe there's a few here tonight as well, or today as well. We have a business entity in Australia. We don't have any people there. I used to live there for 3 years, so I've got a little bit of Australia background. We do have an ABN number, a bank account, so we can invoice and have a work cover and all the good stuff, just like as if I was living there. So we're set up to do business for Australian users. Again, we're a lot of inspect, analyze, solve type stuff we do. There's some pictures here showing that. If you can see my cursor, that is a picture of me 2 weeks ago looking at a link pipe crack in a lower crawl space on a reheater. Above that's an engineer flying a drone to look at some burner problems. This picture shows Hui, our engineer from Vietnam, with an ALS guy in Malaysia checking out some high temperature piping for creep and voids and cracking. And here's a picture of Evan in an ethanol HRSG. That's a waste heat boiler in an ethanol producing plant in the Midwest USA, converting corn into fuel. And Evan's giving a presentation later today. From that inspection results, we end up doing a lot of analysis work. And from that analysis work, sometimes we end up providing hardware that helps solve the problem. Below is three key people here, myself, Evan, and Hui. Each of us are in this conference today. So a few fun facts. Back when I lived in Australia, we did a HRSG Academy in Melbourne, Victoria in 2008. And I see 2 names, maybe there's more, that are online today that were there in 2008. So a shout out to Wim Belgraver and Emmett Beal, because I see your names on the list and I remember you guys from 2008. And we had a lot of fun then too. And then in 2009 was the first ABHUG meeting. So there's Barry and Bob on the left, and there's the group photo on the right. I'm not in the photo because I took the picture, but there's David Addison and Barry and a bunch of and Bob and maybe some other you guys that are here again. I see Anita in the back. Hui does some of the similar work in Vietnam. He's doing training, HRSG Academy type training courses in Vietnam. So we're exposing people to our lessons learned there, but we're also exposing Hui to American stuff. So we bring him back to USA quite often. Here he is trying to ride a horse in Wisconsin. And here he is checking out a an American muscle car from the 70s, drinking a bottle of beer like a typical American in a giant garage full of tractors and cars and boats and snowmobiles, like a typical American here in Minnesota and Wisconsin. We're trying. We don't have him converted yet, but we're trying. And he's based in Ho Chi Minh, Vietnam. Evan's giving a presentation later today. I asked him to send me some adventure photos. All he has is photos of him and his wife and his dogs. He's a newlywed, so I think that's why, but he's got some pretty impressive photos. So here he is in Colorado, where he now lives. He's from Minnesota. His wife's from Minnesota, but they decided Colorado was a better place to live. And we can do that with HRSD because we end up traveling a lot and working. So it doesn't really matter where we live. We're typically traveling to power plants anyway. So some fun photos from him from Colorado. I tried to be Australian. I'm not very good at it, but I tried last Sunday in Florida to surf with my daughters. And we had an instructor, and you can see the waves are very, very small, and I did poorly. I'm still stiff. I also tried a mountain bike, but I don't do nearly as well as David Addison and Armand Durant. And I know they're on the call tonight, and those guys are biking 50, 60 kilometers a day, and I bike maybe 10 kilometers in a day. And so, but I'm trying. So back to what we do. We do a lot of inspect and analyze solve. We're in over 280 HRSGs a year. So we see a lot of things that work and a lot of things that don't work. We try to provide good recommendations to clients and share those lessons learned. And then from that, we can use those photographs and the drawings and the dimensions and the failure history and the knowledge of what worked at another plant or other plants to help with make recommendations and improvements. And this, I need to give credit for ALS for this image on the bottom right-hand corner. They help us a lot with drum cracking, some drum crack analysis work. So we partner on that a lot. And that image is from one of their reports to our client. We do a lot of solutions that involve hardware. We sell a lot of access doors. Sometimes those doors are not to enter. It's just to reach through to look at fragile areas like tube to header joints on reheaters or HP superheaters. Or we've sold some doors in Australia just to get tube samples from the HP evaporator out, because the row of tubes we want to sample is not accessible because of a superheater right in front of it. And then we do a lot of gas baffle work, and sometimes we replace the entire walls of inlet ducts or all the liners and insulation in an inlet duct or a firing duct. Those are great projects for us. One more slide after this. We do a lot of roof casing retrofits. So as these HRSGs get older, it seems like Module 1, Module 2 roof casings deteriorate because of the weather, because of the heat, because of the failing pipe penetration seals. And so those are pretty complicated projects. We call them puzzle pieces that we come in with to try to retrofit those effectively. We do a lot of pipe penetration seal work where we take off the old pipe penetration seal and put on something better that hopefully is more durable. And lately we're doing a lot of drum door manway upgrades where we're making them safer and more reliable using Belleville washers and different hardware that's easier to open and close the drum doors, because we know how important a good seal is on a steam drum and how that can really cause problems if they start to leak during startup. And then sometimes we end up replacing the entire pressure part assemblies. But this is an economizer going into an HRSG in Canada. So that's a real quick overview. Again, there's the names of three HRST people on today. You can reach out to any one of us to ask questions later. And that's it.
Thank you, Lester. Lester, being in Florida, I have to tell you, trying to surf in Florida is like trying to alpine ski in Kansas. So you might have been in the wrong place. It might not be you. It might be the location.
No, I can't handle anything except for Florida. I need those tiny waves. I'm too old and too fragile. I was stiff. I was stiff bad here this yesterday. Did that on Sunday.
Oh, good. Well, thank you. Thank you much. Rob Collins, you're next with your special 10 minutes.
stuff. Thank you guys. Just wait for permission to share.
Hey, Rob.
Hi, how are you doing? There we go. Okay, you see that okay?
Yeah, looks fine.
Okay, great. So just quickly, I'll say thank you to the organisers for the opportunity to share a little bit about RTR today. It's great to be involved and hear about the challenges and the issues that sites are facing. Some of you will know RTR as a supplier, some of you won't, so it's a good opportunity to introduce us as well. We're an independent supplier, steel pressure parts to the global energy industry for over 50 years. As I said, we're independent, active since 1969, supplying coal, coal fleet, CCGT, CHP, and biomass. Doing work in solar now. Waste to energy is a big growth industry for us, and we see that way in Australia as well in the future. And although aware that there's no nuclear here in Australia, however, it's certainly a very tenuous and difficult market to supply to. So I think it gives a good indication of the level of technical acumen that the company has. We have extensive experience in the supply of boiler efficiency and environmental upgrades. We offer a solution-based approach by supplying the most suitable product and material grades from a vast network of supply chain partners. We are a carbon neutral company and have been for over 10 years. And RTR and all of our supply chain are ISO 9001 accredited. You can see here some examples of the companies that we deal with, some of which I know the attendees today are part of, and obviously overseas as well, a number of other companies there. And there's a gap here a map here on the global customer base that we have. And regardless of where our client base are in the world, we'll always make effort to go sit down face to face and meet and understand what the unique and bespoke challenges are for our clients in each site. Our global locations here, you can see there, Ratingen in Germany is our head office. I represent the Newcastle office in the UK. There's an office in Poland, a strategic office in Rybnik in Poland. Obviously, the Melbourne office here in Australia is where I'm located. And we're strategically located across Europe to source from a comprehensive supply chain, some of which our suppliers we've been working with for more than 20 years. That's forge masters, pipe mills, stockists, fabricators, everything. The product range is very varied for the various applications in power gen. We offer main steam, hot reheat, IP, HP, loop pipe work in CMV, 2.25% chrome, 9% chrome with GT26 turbines and CCGTs. And that's pipe work for partial refits to wholesale steam line replacements. We do an awful lot of work with weld elimination with integral forgings, and I'll just point you to a number of photos here, just to make the point that the manifold T here, the reheater strainer body at the bottom there, and the spools with the inlet and outlet branches, all of those branches, all these parts are completely seamless, integral design. There isn't a single weld on any of those components. We also offer the associated pressure fittings and elbows and pipe hangers and supports for these contracts. Fully fabricated water wall, induction bending as a major part of that and what we do as well. And as we're developing, we're doing an awful lot more work in explosive, roll bonded, weld overlay clad products. And all of this is supplied in accordance with bespoke and technical requirements in accordance with clients' needs. Our product range continued is just, seamless boiler tubing, welded boiler tube, steam gas pipelines. We do an awful lot of rolled and welded spools for bypass and things like that as well. And all of this is in carbon steel through to high alloy. I'll just direct you to another integral photo here. That's a large diameter pipe and separate reducer that we proposed as an integral part, and we actually supplied as a seamless component that you see there. Also the attemperator fabrication there on the right hand side, machined tube sheets and some more forged straight spools at the bottom there as well. So through collaboration and consultation with our clients, we'll source the most appropriate and compliant solution to meet your bespoke needs. We don't have any, we'll have a little bit of critical stock, but our main focus is to supply and source from our supply chain to meet exactly what you need as the client. We take care of the complete material supply from project inception through to delivery at site, and that's all taken care of. DDP delivery, global and international logistics, full traceability, documentation control, quality assurance, all, as I say, through an ISO 9001 certified supply chain. A little bit more detail here on our weld elimination and the work we've been doing. Obviously a fantastic opportunity to improve plant life and boiler efficiency. Products include tees and bifurcations, integral nozzles and stubs, branches, a complete elimination of type 4 cracking and crack propagation by eliminating the welds. The benefits in terms of optimum longevity, the reduction of welding, not to mention the fact that you're saving time on installation as well, and the reduction of continued observation of welds that no longer exist. And the initial upfront cost for a forging can be higher, but the long-term cost of running as part of the plant life can be significant saving. And just to give an example, again, this double branched forging here, the T that we did, that was actually machined with a bend to allow for the fact that the boiler had sunk in its foundations on one half in service. So it really gives an indication of the level of flexibility that we have with these designs. And again, to reiterate, this is completely, all of these parts, even 8-meter long spools like these, are all of completely seamless design, manufactured and forged from one piece of steel. As I said, we see waste to energy as a real growth. In the UK, for 10 years, we've been supplying waste to energy. It's gone from a handful of sites in the UK to more than 100. We're aware of 2 sites being built in Perth as well, or around Perth. And you can see the products that we offer in terms of the panels and tube banks, swaging. This is all carbon steel through to high alloy, and then we're getting involved, as I said, with the overlay, which has fantastic corrosion, oxidation and abrasion resistance. And again, you can see some examples here of some of the external cladding overlay that we've been offering. I've already mentioned our ISO approvals, the carbon neutral. In the UK, we're also an Achilles registered supplier. And in 2019, specifically in recognition of our growth in Australia, we were awarded the Queen's Award for Enterprise in the UK. We've gone from a 0 turnover 7 years ago to a well over 7 figures that we do now on an annual basis in Australia. And finally, I'll just wrap with a few case studies, some of the work that we've done. This is an Australian power station, and we've had an umbrella agreement for a number of years. And that work came to an end last year with hot reheat and main steam pipeline replacements. Awful lot of integral forgings, as we've discussed, induction bending, integral forged T's, elbows, a full suite for virtually a full replacement of CMV in chromoly materials. This is one of the largest forgings that we've produced in our company. You can see this double branched 5-ton reheater strainer body, the machining involved to produce the finished part, produced with an integral reducer, eliminating the weld setup that was previously in place. And this is all manufactured to extremely tight tolerances, plus or minus ½ mil to manage weight. And also there's been thousands of dollars spent on the technology to machine the internal radii on products like this, smooth and completely contoured to eliminate those stress points of sharp edges that you see. Another one water wall panel projects that we did. This is actually all strip membrane welded 16MO3 grade and then formed together. But we do offer it as a pipe extrusion as well, which tends to be the way it's supplied here in Australia. So a longitudinal extruded fin, which is then all welded up into the panels. And as things develop, we're seeing an awful lot of work in GT26 turbines, particularly in the UK, where there's been a lot of issues with type 4 cracking, weld degradation, creep fatigue and thermal shock. So we've done an awful lot of work in 9% chrome, supplying, for example, this integral forged T for manifold spools, reheated outlet manifolds, done an awful lot of bypass work, OTC tubing and temperator fabrications. And we would encourage anyone with similar setups and the GT26s to come forward and have a chat with RTR, as we may have been producing products that meet your requirements. And then finally, on an annual basis, we're working on 250 tonnes a year annually of boiler tube supplied into Australia. This again is for 1 or 2 stations that we've been doing a lot of projects with in various EN, ASTM grades, 1% chrome, 2.25%, 9%. Anything really from carbon steel through to the high alloys, and some of the applications there that we've been supplying against. And that is all. Thank you very much, and hope to hear from you if you have any requirements we can support with. Thank you.
Thank you, Rob. That's some pretty amazing looking stuff you described.
Thank you. Yeah, I'm never shy of an opportunity to wax lyrical about the work that we're doing.
Yeah, it's amazing. Hey, Barry, we have a few minutes before before the end of this question period. If you have some more,
Go ahead, finish off yours. There was
Barry, your volume is very low.
There was an indication that Ori wanted to speak, Bob.
Yeah. Ori, you want to unmute yourself? Barry, your volume is still weak.
Yeah, I don't know what's happening.
It's my volume.
You're fine, Ori. Go ahead.
Great.
Okay.
Yeah, thank you.
Introduce yourself.
Ori Selzer. I'm with IMI CCI, and so I've been speaking to Ben a little bit about his presentation and the attemperators and the nozzles, and then had some comments, and then Lester kind of led into it too with his comment about liners and performance of nozzles. So I just wanted to say that, and I don't want to speak for other suppliers, but our recommendations and requirements on liners are associated with application and by application. And so those bypass valves, of which Ben showed that he had the majority at his facility in his steam turbine bypasses and his HRSG bypasses to the ACC. If running properly, that type of application should not have to spray water. Or how should I say it? It should always have to spray water when steam is operating through that system. So that would suggest the opposite is true, in the sense that you should never bake out the system and have hot steam flowing with no water present, because the downstream system is a condenser and it must always be cooled. And so when we have those types of bypass systems, the theory is a liner is not needed, because you should always be cooling. Like, you should never have an opportunity where the downstream piping will be heated with no water spray and then you'll be initiating. Where in an interstage attemperator, you could have those types of scenarios based on surface area in the boiler, load of the GT, all of that. You may have situations at base load where you might not spray any water, and your attemperator could sit for hours and reach elevated temperatures. And so the pressure boundary, the pipe spool would reach elevated main steam temperature, and then you'd initiate spray. And so that's where the liner is a requirement and not a recommendation. Where in those bypasses, anytime steam is present, you should always be spraying. And so in theory, you should never be elevating that downstream section to high temperature and then initiating spray. Now, to Lester's point, that's all in theory. In practice, you know, that's a different story. In practice, you may have a lot of initiation of spray when that steam pipe is at elevated temperatures based on leakage or other operational issues. So, but it's just kind of a food for thought in terms of a supplier's view of when a liner is needed. And it comes down to cost. I always say it just comes back to cost. So not putting
Is
it.
it,
Anyway.
Ori, is it safe to say that if the owner wants to really, you know, have belts and suspenders, if they spec a liner, then the competitive cost issue is at least neutralized. I mean, the cost doesn't
Yes.
go away, but the various bidders then are all on the
Absolutely.
same plane.
Yes, and you know, a liner on a typical bypass valve where you have that spray system on the outlet of your bypass valve, any liner is going to add, you know, a meter of pipe, if not more, and you could be 9 chrome, could be 22. Either way, it's still, you know, expense the liner itself, the way you're attaching it, and then that added pressure boundary is all just cost. So if you are going to spec it, also don't just say must include a liner. Get a little specific. Learn what you want, how long you want it to be, what thickness you might want it to be. You know, if you're going to take the time to spec that you want a liner in that system, be specific on what you're asking for. Otherwise, you might just get somebody that puts some aluminum foil in there around the pipe or something. So,
Okay, good.
Good.
thank you.
Okay. Thank you, Ori. So Bob, I think we're ready to change over and go
Okay.
into the second part of the session.
Okay,
My sound is-
we're gonna go for some chemistry, folks. I know that
Yeah.
thrills most of
Yeah.
you.
I've got a couple of announcements though first.
Go
Oh,
ahead, Barry.
Hold on, Bob. Yeah, we have a couple of minutes, so I just wanted to mention about if any we usually share the list of attendees with email addresses. If there is anybody that doesn't want to do that, please send the people from Mecca, that's Heather and Rachel, a note, and your name will be taken off the list. And the second item is for the presenters. We usually allow a week after these conferences for you to provide a final version, which would then be the version in protective form that would be put on the website. So just let us know in a week. Just send me the final copies. Thank you. And now we can move ahead to one of the important, probably the most important. You saw in my presentation yesterday how the instrumentation, the cyclochemistry, is the leading repeat cyclochemistry situation, is one of the leading things that leads to a failure, is not having proper instrumentation. So we asked Kirk here to provide this presentation. He also provided a slightly longer version at the HF that Bob and I ran a couple of months ago. So Kirk, over to you, please. Thank you.
You had it, then it went away.
Okay. Can you hear me now?
Yeah, we hear you.
Yeah,
Your
all
full
right.
screen. Your full screen went away though.
Yeah, I'll get it back here.
Okay.
Just takes a minute.
It's got a long way to go.
Yeah, I guess so. Well, hello, everybody. Kirk Beesher here from Mettler, Toledo. Hopefully, I'll be full screen here in just a second.
There you go.
Global Director of Mettler's Power Instrumentation and Analytics business. We're also a proud sponsor of this event, have been working with Bob and with Barry at different events and different conferences over the past, and happy to continue that. I also want to thank the steering committee for asking me to make a similar presentation to one that I made at this HRSG forum this past summer. So as you probably gathered, both Barry and I are working the night shift. It's about 12:30 at night for me. I'm in the hotel room in Switzerland. And if I get a little tongue-tied, it's just because I'm tired. Barry did a great introduction because this content and this material really does address that issue of repeat cycle chemistry and one of the leading causes of that. Let me just go into this with a little bit more of an intro here. This is a non-commercial presentation. However, you're going to see a lot of photos and images of Mettler-Toledo's power plant, SWAS panel related analytics. Our commercial presentation is going to be tomorrow as part of a sponsor of this event. So I'm not going to talk about pros or cons of one analyzer over another, but I did want to highlight that there are going to be some images here, but those are really representative images. Those could easily be SWAN products or HAWK products. I'm also going to go through the first section fairly quickly, just touching on a few highlights of those slides as we go through that. So starting with kind of the background of where this material came from and why it was needed, again, Barry and I have both touched on this, is far too many plants, particularly aging plants or in some cases even newly built plants, are poorly managed, poorly maintained. They have equipment that's offline, needs repair, or they never had the right instrumentation to begin with. So to really kind of drive the point home that a happy, healthy, successful power plant really needs the eyes and the ears into the water and steam quality to really do a good job staying on top and preventing problems before they get more serious and before they cause more damage and before they get really more expensive. This concept, this material that I'll review here was really developed by the IOPS Power Cycle Chemistry Group. Again, that's a global group. We hope to get as much participation as we can. There's a strong group in Australia and New Zealand. I know there's some folks here in the Asian region as well. Love to have you on board as part of IOPS and in the Power Cycle Chemistry Group. All the members that contribute to this, not only are they part of this group, they also have ties to organizations like EPRI, VGB, some of the standard organizations like ASME, ASTM, academic groups, and other manufacturers, suppliers of boilers, turbines, water treatment. So a really well-established, well-rounded group. And that group developed and continues to develop and upgrade this technical guidance document that really lays out and specifies the minimum analytical equipment really required for these happy, healthy plants. So these standards, these documents, these recommendations were really developed with the following points in mind: is you should have at least enough instrumentation that you can pinpoint the parameter, the driver for each failure mechanism that can occur in that plant. But you can't be just single threaded. There needs to be some redundancy there, and it needs to provide more sensitivity, more of a holistic view. So one instrument should be able to also represent a problem, a failure in the cycle if one goes down. So if a unit goes down, or if something's out of service, or something's needs to be calibrated, or an analyzer's out of reagents, there has to be at least enough redundancy built in that the operator is not questioning the accuracy of the analytics itself. They've got to believe that it's a water problem. So there's got to be enough redundancy built in so that the first response is, oh, there must be a problem with that sensor or that transmitter or that analyzer. So we've got to get beyond that, and that's why we need the redundancy. And that also relates to this idea of trust. So there's got to be trust in the results, the feedback from the analytics. And this touches on some of these concepts that you've probably heard: smart analyzers, smart alarms, verified alarms. Those are all concepts and talking points around the analytics and how those analytics can provide and raise the level of trust. And then, of course, those analytics, especially these critical few, need to be correctly alarmed, they need to be audibly alarmed, and they need to trigger a response in the control room. They need to trigger a response and a signal through the DCS and PLC. I probably, pre-COVID, visited somewhere between 40 and 50 power plants a year all over the world, and I'm still surprised by how many sensors, transmitters, analyzers that are just standalone. They're not connected to anything. So if you're not standing next to the transmitter or the analyzer when the alarm goes off, you could go hours before anybody caught the problem. So quick overview of the key instruments. Again, these key instruments are defined by this document. Just a basic overview on specific or direct connectivity. Obviously, it's non-ion specific. I think really the key point I want to make here is with connectivity, temperature compensation is really critical. And you want to make sure that it's set correctly, it's configured correctly to the appropriate measurement location in the plant. I've included some of these slides. I won't go into all the details, but you guys paid good money for this material. I want to make sure you get good value out of this. Even if you review it after the fact, you can catch up on this. Now, the next type of connectivity is cation connectivity or acid connectivity. You know, one thing that you need to think about a little bit is once you looking at that measurement, now the resin column has become part of the measurement. So really maintaining the sample temperature again to avoid any sort of damage to the resin, monitoring the rate in which it's exhausted, particularly if you're running high levels of ammonia, that resin's going to exhaust quite quickly. Because it's part of the measurement package, part of the key thing to manage is you've got to stay on top of that resin replacement and regeneration. You don't want it to exhaust and then trip false alarms. pH, as most everyone who has dealt with pH in pure water knows, it's a critical measurement, but it's surprisingly difficult. Measuring pH in low connectivity, very pure water is really problematic. You have to use the right pH electrode for the job. It's got to be designed for pure water, low connectivity measurements. You really should probably avoid any sort of measurement system that relies on flow bowls, because unless you're really vigilant on keeping those flow bowls clean, you pick up a lot of particulates, a lot of corrosion particles in those flow bowls, which then interfere with the accuracy of this very sensitive pure water measurement. You got to stay on top of calibration, and wherever possible, back up that measurement with calculated pH or derived pH. It's a critical measurement. You know, much like the old saying, measure twice, cut once, it applies to pH. Measure pH, two different technology simultaneously, and monitor the relationship between those two measurements. Dissolved oxygen, as you probably all know, too high is bad, too low is bad. Especially low is risky when you're using a reducing agent. There is some new technology on the market, this optical based technology. Some vendors call it LDO, we call it ODO, but eliminates the traditional polarographic membrane, which reduces a lot of maintenance, reduces the frequency of calibration, gives you a faster measurement, a more accurate measurement, and it's really kind of the trend in the industry where a lot of people are going nowadays. Sodium, you know, this is a critical measurement, particularly for any plant that is seawater cooled or has a high level of sodium in their raw water. The fundamentals here are you're using DIPA to prevent interference with that measurement. You really would want to choose an analyzer that has automatic calibration as opposed to those with manual calibration. When it comes to phosphate, still a lot of plants are using phosphate. The recommendation is it should be trisodium phosphate at 3-to-1 molar ratio to really avoid potential damage being caused by the phosphate dosing and or just chasing phosphate hideout problems of overdosing and underdosing and swinging back and forth. So historically, some older analyzers really struggled. Online analyzers for phosphate honestly weren't that good. They weren't reliable. They had high levels of reagent consumption, high maintenance requirements. A lot of plants tried them, got frustrated with them, moved away from them. But I'd encourage you to take a look at some of the newer technology that's out there. It's really much better than it's been in the past. And it avoids the infrequent measurement that typically goes along with grab sampling. ORP, that's an optional measurement, but really important. It's a key measurement if you have any copper alloys in your systems. Just some notes here is there are standalone ORP sensors. There's ORP sensors that are integrated with a pH electrode. Calibration is really important with ORP sensors, but unless you've gotten some training on it or just really built up some experience, a lot of people calibrate ORP sensors incorrectly. And then the placement of that ORP sensor is really critical when you're measuring ORP relative to the scavenger measurement. So too early, too late relative to the scavenger dosing pump is going to give you incorrect readings. You got to do the calculations to determine that your ORP sensor's in the correct location. So that was a quick overview of the required analytics. Now some of the recommended or optional degas cation connectivity. It really solves for that unknown of what is the contribution to your cation connectivity based on the CO2 that's in the water. So you want to, that's a particular problem for fast start plants. That's a particular problem for cycling plants. You absolutely can start your plant faster if you have degas cation connectivity because it eliminates that unknown. It gives you the confidence that you have the proper water quality and ultimately the proper steam quality to start up your plant and make sure your steam quality is in good shape. So the other optional measurements here are silica. Sometimes I'm really shocked that silica is optional. Most plants use it. It's almost a default. It's considered optional because if your raw water has low silica level, you have excellent and you can maintain and have good maintenance on your water treatment system. You can get by with some periodic grab sampling. I personally wouldn't recommend it, but that's your choice. Again, there has been some knocks against silica analyzers in the past because of reliability or high reagent consumption or high operating costs, high maintenance costs. There's really some new analytics on the market that eliminate that and could really move from optional to recommended if it really is low maintenance, low cost to operate. Total organic carbon, another recommended, optional, not required. really critical for those cogeneration plants, pulp and paper plants, refineries, chemical plants, wherever you have a real high risk of organic contamination coming back with the steam condensate. Highly recommended in those situations, and it can really prevent those organics coming back and quickly wiping out the resins in your condensate polisher, or without a condensate polisher, going into your boiler and breaking down into organic acids. So why are we measuring this? Where are we measuring it? Got some comments here. We're just going to go around the water treatment cycle here, the boiler steam cycle, starting with connectivity. Again, in the makeup water, you want to measure that as it comes out of your water treatment, upstream of where it mixes with your returning condensate. Then cation connectivity, you want to measure that in the condensate stream. So you have good insight to the quality of the water coming into your boiler steam cycle, returning from your condensate. And if you have a problem, you know where that problem is sourced. Again, some of the optional measurements here, silica and TOC. TOC is particularly important if your raw water comes from natural rivers, lakes, streams that have a lot of organics in it. Particularly a problem in Southeast Asia, places like India. They really struggle with building water treatment systems that can remove all those organics prior to it going into the rest of the cycle. On the condensate, you want to measure at the condensate extraction pump discharge. This is going to be the first warning point of a condenser leak, or whether or not you have some regeneration chemicals from the makeup water plant coming on over. It'll tell you whether you've got contaminated condensate from your storage system, gives you an indication of whether you've got air in leakage. Here you want to measure cation connectivity, sodium, dissolved oxygen. Then the optional, but really, really helpful and part of this holistic view is pH. And if it's a plant that starts up rapidly, fast start plant, again, degas cation connectivity. Now, if you have feed water with a condensate polisher, at the condensate polisher outlet, you want to be measuring cation connectivity, and you want to be measuring sodium for the reasons that are outlined here. Optional, optional is in addition to cation connectivity and sodium, just a standard specific connectivity measurement as well, as a kind of a backup to that sodium analyzer. That's where you get the redundancy. Maybe your sodium analyzer is out of service, maybe it needs calibration. It would be highly recommended to have that specific connectivity there as a backup. Feed water without condensate polisher, again, you want to be making these measurements downstream of the feed pumps, specifically on HRSG plants. You want to be looking at connectivity, cation connectivity, pH, and dissolved oxygen. Those are all the minimum requirements at that sample locations for this, for these reasons. I'll point out the comment on dissolved oxygen. Where you're dosing oxygen to the feed water, you really have got to verify you're maintaining the correct dosing of the oxygen. And then again, if you have copper alloys, this is where you would want to use your ORP or your combination pH ORP sensor. Now, for plants running AVT, no alkali, connectivity, cation connectivity, pH are all the recommended, those are the minimum requirements. The optional would be the silica. And again, you can see the reasons here for that. If you're running drum boilers, you've got a drum boiler, HRSG evaporator, you're running caustic. Now, very similar, specific connectivity, cation connectivity, pH, and the optional silica. And note that Silica is less volatile in boilers with caustic dosing than ABT. So if you have a choice, where are you going to put your silica analyzer? Where is it needed more? It's going to be needed more on an ABT dosed unit. Now, phosphate, back to phosphate. If you're running phosphate, you don't need an analyzer, but it's a heck of a lot more convenient because you're really trying to address a multi-dimensional problem where by using connectivity, cation connectivity, pH, but based on like the dosing levels, at lower phosphate levels, the pH is going to be driven more by ammonia. At higher phosphate levels, small condenser leaks might not even be noticed based on pH. So pH alone is not a very accurate or very reliable tool in your toolbox. Really direct measurement of phosphate, either taking grab samples back to the lab or with an online analyzer, is really a much better way to go to really avoid the headaches of the phosphate hideout and return that little graphic is highlighting. On plants running phosphate, to kind of continue with this thought, again, direct measurement of phosphate, optional sodium, and optional silica. Again, as these analyzers become more reliable, less maintenance, less cost, less consumables, it really makes more and more sense to let the analyzers do the work instead of relying on grab sampling, which I'm sure you've heard Barry say multiple times is not the way you want to run your plant. It's not the way you want to make serious decisions based on grab sampling and lab measurements. You really need to let the online analyzers do the work. Now, silica and steam and protecting the steam turbine, and really, what are you measuring here for steam quality? You want to protect the turbine from carryover. We talked earlier about a temporary contaminated, temporary spray water, and you want to avoid swings or increases in silica. There's been a lot of talk here recently, at least that I'm hearing, again, Southeast Asia, India, around colloidal silica and the problems that's causing. But you got to base your measurement on appropriately designed and appropriate located sample extraction, and you've got to have the right probes. And where do you measure? You want to measure upstream of the superheaters for a saturated steam measurement. You want to do downstream of the superheaters, and that's going to catch the contamination for the attemperation spray. So those are a couple of different options there. Really, with the lower cost of multi-stream silica analyzers, measure both. And I think what I'll do here is just show consequences of not having minimum instrumentation, not measuring what you should be measuring, where it should be measured, and letting things get out of control. Eventually, your steam turbine starts to look like this. So nobody wants that to happen. And analytics is a really good way to prevent that in the future to happen to your steam turbine. So wrapping up here, really as we talk about superheated and reheated main steam, cation connectivity, sodium, and the measurement locations here, silica, again, if it has non-reactive or colloidal silica, that often varies with the season. The optional is the degas cation connectivity in your steam, again, verifying that the steam quality is up to snuff. And that's a quick overview of the minimum instrumentation required and recommended for happy, healthy, long life plants and avoiding these repeat chemistry alarms that Barry talked about last night, yesterday.
Good, thanks, thanks, Kirk. If Bob has one quick question, we could have that.
Yeah, go ahead. Go ahead, Barry.
Oh, okay. I thought you were going to do it. There's one from Greece, Yerevan, Kirk, and he says, can you touch upon iron measurements required?
Yeah, so if you haven't seen it, I'd highly recommend you go out to the IOPS website. There is a technical guidance document on iron measurements. There's a lot of discussion, maybe a little bit of controversy on different types of iron measurements, whether you're measuring total iron or particulate iron. Now there's a bit of a trend in the industry to use turbidity, and in some cases even particle counters and particle sizers as really substitute measurements for total iron. IOPS recommends that a true total iron test be made. We're looking at making some updates to those documents in terms of where to make measurements, when to make measurements, but iron measurements are particularly key. And they're very important for cycling plants and plants that are changing loads frequently. I think this is one area that I think we need more investment from vendors like our company to provide easier measurement solutions, more complete measurement solutions for iron, total iron, or substitute measurements. Barry, would you add anything to that?
Yeah, Kirk, I think because you missed the session yesterday, we covered the IAPS document.
Oh, great.
And I also mentioned about the white paper for fast start and flexible plants. And I offered to send it to anybody that wanted it. I've sent it to quite a few people, and I offer it again if anybody wants to see the very latest on measuring iron with proxy techniques and sensitivity control. Then you can see it in this. You can see it in this white paper. And thanks very much, Kirk. There is another question, but we'll go on because we have a discussion session at the end. So thanks very much, and
Okay.
we'll move to the second from Evan Almberg at HRST, already introduced by his colleague Lester. And Evan, if you're there, you can proceed, please.
Yes, thank you, Barry. I'm looking here to share my screen. I believe everything should be showing now.
Looks
Yes.
good.
Yes, it's good.
All right, thank you. As Barry introduced, my name is Evan Alberg. I'm an analyst engineer with HRST, and my primary role is in thermal performance and failure analysis of gas turbine HRSGs. So today I'd like to discuss some of the effects of gas turbine upgrades that we've noted in the last few years, and kind of highlight on some of the more typical issues that we see that regarding performance, operation, and reliability. So over the course of the last few years, gas turbine upgrades have been pushed quite hard by many of the GT OEMs. One of the primary motivators for this is increased plant efficiency. One of the examples I'd like to show here is for a 9FA.03 compared to a 9FA.05, where the combined cycle efficiency increases roughly 1.5% from about 59.5 up to close to 61%. So it's a significant improvement, and it's a primary motivator both economically and in order to respond better to the grid. Some of the primary modes that it increases flexibility is that a gas turbine upgrade will allow faster gas turbine starts, allow lower gas turbine operation or lower load gas turbine operation, and it can improve the peak power output. Particularly in today's power industry, being able to respond to the grid faster is a huge factor for many combined cycle plants that are aging or potentially being built and need to have a higher motivator or a higher grid response. So this could be to respond to the flux in renewable generation or the loss of megawatts from base loaded coal assets. And being talked about more and more frequently now is fuel flexibility and being able to be hydrogen ready, being able to blend 30%, 40, 50%, and ultimately 100% in the future. So with a typical gas turbine upgrade, you're looking at changes to the exhaust gas flow rate, exhaust gas temperature, and the exhaust gas energy. Overall, it's typically expected that you're going to receive somewhere between 3 and 10% increase on the gas turbine power output. The heat rate will decrease by somewhere between 0.5 and 1.5%. And on the exhaust gas temperature side, you're looking at a plus 28 degree C at baseload temperatures. This can also increase the exhaust gas mass flow rate, roughly 2%. And you're going to experience higher exhaust gas temperatures during startup, and particularly at low load. Typically 649, 650 C is the maximum that is stated by the OEM. Sometimes there's a little bit of variation by roughly 1 to 2 degrees. But the primary question and that we're going to go into today is how is this going to affect the HRSG? So some of the key concerns all stem from those 3 items that I discussed on the previous slide: energy, mass flow rate, and temperature. Exhaust gas energy is going to increase the amount of steam flow, potentially exceeding the HRSG rated capacity. It could also reach safety and relief valve set points, as well as separator designs. The temperature specifically is going to become an issue for superheater and reheater tubes, non-pressure part overheat, a temperator operation, and emission compliance. And then the exhaust gas mass flow rate itself, which plays into the temperature and energy as well, can alter the performance of catalyst or gas side pressure effects throughout the HRSG. Well, there's a lot of topics that we could discuss. I'm just going to highlight a few of the major ones today, which is tube metal temperature and overheat, a temperator overspray, rated capacity, and balance of plant considerations. So the first one that I would like to discuss is tube metal temperatures. Base and low load are going to experience a significant increase in the turbine exhaust gas temperature, and you're going to experience this temperature increase earlier in the curve. So this example to my right indicates that pre-upgrade, the gas exhaust temperature at negative 30 degrees Celsius, so the very cold ambient temperature, was roughly 615 C. But after the upgrade, it increases nearly 30 degrees C to 645. So it's a notable change. And as well, as you can see on this curve, the post-upgrade exhaust gas temperature is going to reach its maximum temperature sooner than what the pre-upgrade gas turbine would. So this really plays into the tube metal temperatures, and they can be a limiting factor from an operation standpoint. And this is extra important for HRSGs that only have a final stage or a terminal point attemperator, because they're unable to actually control the HP superheater or the reheat temperatures. And one thing to note as well is even if the tube metal temperature design limit is not exceeded, the service life of that pressure part could be affected just by operating at that elevated temperature and pressure. One of the more simplified ways that we can look at this without performing a complete remaining life assessment is doing a comparison using Larson-Miller parameter and looking at the creep life approximation for tubes. So I have 2 examples here to my right. The first one is a grade 22 tube, which can typically be attributed to a reheat tube. And you can see here along this curve that the tube metal temperature, by having a very small increase of roughly 5 to 6 degrees C, decreases the lifespan by roughly 85,000 hours, or a 31% life decrease. And this is right in that temperature range that typical reheat systems operate. For the second example, which is looking at a grade 91 material, typically an HP superheater tube, could be a reheat tube as well. Another fairly small change, roughly 5 to 6 degrees C, decreases the lifespan by roughly 41%. So when you're at these elevated temperatures, even a small increase in operating temperature can have a large effect on the lifespan of the part. We'll look at a couple examples here. Typically with tube overheat, you want to focus on module 1 tube panels immediately downstream of the gas turbine, or if you have a duct burner, then module 2, and looking at those tubes immediately downstream of that. The area that we typically like to put a lot of attention to is nested grade 22 superheater or reheater panels. And the reason that these tend to gain a lot of attention is because the exhaust gas temperature at those locations is very similar to what the grade 91 material is experiencing. But during startup or low load cases, the flow through the reheat system is notably lower. So this increases the tube metal temperatures and the header metal temperatures at these locations. So one of the best ways to look at this is just do a detailed visual inspection to identify if there's any issues that are occurring. You can see this exfoliation that comes about on these grade 22 tube stubs. This would be the steam outlet where you would expect the highest operating temperatures to be. And just to look at some more aggravated versions of the scaling. So if you do find notable scaling and issues like this, a remaining life assessment can be used to help determine what the used up lifespan was and what the available service life is as you move forward. So just a couple of ways to address tube metal temperature overheat. We discussed a few already. Periodic visual inspection of the tubes, external visual inspection, and internal borescope inspection, looking for any signs of oxide growth on the interior of the tubes. Thermocouples mounted to the tubes is a great way to monitor them. Typically, you need quite a few in the HRSG spanning the entire width because oftentimes a thermocouple will tend to fail. So being able to have that redundancy can give you that confidence that you're operating at the correct temperature. If there are indications of overheat that have occurred, there are some NDE field testing methods that can be done. Magnetic particle testing, looking for any signs of overheat and cracking that could occur. And then as well as ultrasonic testing and some advanced NDE shear wave phased array. And in some cases, particularly for grade 11, 22, and grade 91, metallographic replicas can help determine if there is creep damage or an onset of creep within that material. And like we discussed, if there is overheating, performing a remaining life assessment can help determine how much life has been consumed, how much remains. And if you do have an HRSG where there's only a final stage or terminal point attemperator, you may need to attemperate the exhaust gas going into the HRSG, or consider retrofitting the an interstage attemperator within the HRSG so you can accurately control those HP superheater and reheat panels to their design temperature. Next, I'll touch on attemperator overspray and valve capacities. So one thing that we oftentimes see is in the post-upgrade conditions, even though the exhaust gas temperature and energy is going to be much higher, the final steam temperature set point is typically still around 565 Celsius. And the reason for that is the steam turbine is only designed for so much. So we're always trying to hit that temperature, but we're going to have to throttle somewhere because the gas turbine energy is higher. So as the exhaust gas temperature and mass flow rate increases into the module 1 tubes, the typical trend is that as your exhaust gas temperature increases, your spray water flow rate is also going to increase. And while this may not be an inherent issue, one item that you need to look at is that the attemperator or the control valve or even the piping associated with the attemperator spray water line, it could run out of capacity. So that's something that should always be evaluated prior to an upgrade, so you're not limited just due to the attemperator spray flow rate. Another issue that can come about as a result of higher spray water flow rates is that overspray can occur, in which you're spraying down to saturation at the attemperator. So this curve also shows that as the gas turbine exhaust temperature increases, the degrees of superheat, so the degrees above saturation, is going to decrease quite substantially. For this particular graph, which is based on an F-class gas turbine, we're seeing that a 10 degree Celsius increase in the gas turbine exhaust decreases the amount of superheat by roughly 36 degrees. So it's definitely not linear. There can definitely be some issues that could come about from this. And next we'll look at one site-specific example. So this was an advanced gas path upgrade where the GE 7FAs were upgraded from the .03 to the .04 gas turbine package. These are Vogt triple pressure HRSGs in a 3x1 combined cycle configuration. So you can see in the post-upgrade operation, particularly looking at 100% load, even at low load, that the attemperator valves are exceeding capacity in a majority of the cases. And these are extending from typical, ambient conditions all the way to warm ambient conditions through all different facets of operation: base load, max firing, minimum load, and unfired. So for this particular plant, they needed to modify all of the attemperator spray water valves in order to provide adequate flow rates for these upgrade cases that they wanted to operate at. So aside from just changing out attemperators, it's always good to perform visual inspections of the attemperator probe heads, because even though you may not be overspraying, that doesn't necessarily mean that there's no issue occurring within the spray water probe itself. If it's stuck open or if it has an improper spray, it could be releasing liquid water into the system that's not evaporating, and this can quench tubes or even cause cracking on the downstream piping as well. So it's important to do spray pattern testing of the nozzles periodically. You can rotate your nozzles in and out of inventory, so you always have a stock of good refurbished nozzles. And then you can plan to send out the other ones for testing and be returned for the next outage. This is an example from a recent inspection showing that the spray water probe valve head is actually stuck open due to debris in the system. So this was actually leaking water into the system even when there was no spray water demand. And if your valve does run out of capacity, you can look at modifying the valve and the probe for higher spray water rates, or potentially decreasing the amount of duct firing that you have in your HRSG to lessen that spray water demand if you're duct fired. Next, we'll look into HRSG rated capacities. So since the gas turbine upgrade is putting higher exhaust energy into the HRSG that was not originally designed for, it's typical that steam production is going to increase. So this could cause the HRSG to exceed its rated steaming capacity, and that higher steam flow rate going into the turbine could also increase the back pressure through the HRSG, causing relief valves to reach their set points, or if they get close, they can chatter and begin to damage the valve. So if you have an HRSG that has duct burners, one of the best ways that you can control this is by derating the duct burner and backing off on what your firing rate is. But if you have an HRSG that does not have duct burners, you're slightly limited. Without duct burners, you really don't have that luxury of being able to modify how the heat input into the HRSG is, besides altering the gas turbine. Typically, you don't want to back down the gas turbine. For one, you're going to lose megawatts. You're going to increase the plant heat rate. But at the same time, as you decrease your exhaust gas flow rate through the gas turbine, it's likely that the temperature is going to increase slightly as well. So you actually run into low load gas turbine situations. There are some debottlenecking techniques that can be used. HRST uses one called a flex tune, where it allows full gas turbine operation and only really sees a limit on the steam turbine by using steam suppression. And we'll get into two different case studies next, discussing duct firing and non-duct firing HRSGs. So if your HRSG has a duct burner, typically your exhaust gas temperature is going to increase up to the isotherm conditions, which is around close to 28 degrees Celsius above what the pre-existing upgrade would be. And what this does is increases the temperature into the burner inlet. So if you're operating at the existing firing rate, you're likely going to see increased tube metal temperatures downstream of the duct burner. So by using a thermal analysis, you can understand that backing off on the duct burners and what your heat input is can help decrease the tube metal temperatures. And essentially what you do is derate the duct burner by putting in a new limit into the DCS to control what that firing rate or firing temperature is going to be. And one very critical thing to do is pre and post upgrade, since your exhaust gas flow is going to change through the HRSG, is to monitor the flame patterns. Understand what they look like prior to the upgrade, and then monitor them post upgrade, and ensure that they're only that the flame is only roughly 1/2 to 2/3 of the way down the firing duct, in order that it's not impinging on the tubes. So 2 case studies that we have here is 7FA that was upgraded with the AGP upgrade to a .04, and these are the same vote triple pressure HRSGs. For this particular upgrade, both the HP and the reheat nameplate capacities were exceeded in all of the post-upgrade conditions. So decreasing the firing rate was recommended in order to control that steam suppression, or in order to control that steam rate. You can see that the nameplate capacity here for the HP system, and this is in pounds per hour, was roughly 706, and the expected steam flow post-upgrade was 758. So not only was it exceeding the nameplate capacity of the HRSG, but it was also exceeding the relief capacity of the safety valves. So one option that you do have versus backing off on your duct burners is, if you want to maximize the total amount of steam going into the turbine, you can perform an HRSG capacity re-rate, which is essentially more of a paperwork and a study to ensure that the system can handle the amount of steam that you anticipate to be generated. However, let's say your HRSG pressure increases substantially to where you're reaching your PSV set points or even reaching the MAWP of the system. That is a much more complicated issue because the typical panels, tubes, and pressure parts are designed with very little margin as far as MAWP. So increasing that is typically not an option. So HRSG steam capacity re-rate is quite doable, and the pressure re-rate is typically a not feasible option. Next, we'll look at one other case study. This is a 7FA.04 with Neuter Ericsson triple pressure HRSGs. However, this plant does not have a duct burner. So this plant performed the upgrade, but did not do a pre-upgrade analysis. In their post-upgrade, they noted that they were limited on the gas turbines and had to decrease their output because they were exceeding set point pressures and MAWP during full load operation, during typical summer ambient conditions, and especially during cold ambient conditions when the amount of flow going through the HRSG increased. So here we can see that by using a steam suppression system, the maximum potential steam turbine output does decrease, but the gas turbine gain outweighs the steam turbine loss, so it's a net positive. And what this does is limit the amount of steam generation in the system to control the pressure, and that allows the HRSG to essentially operate, or the gas turbines to operate at full load, and you're throttling the HRSG. So in this particular example, we see that their existing megawatt was around 580 nominal. Without limitations, they could reach 600. However, since there is some throttling that occurs on the steam turbine, they were able to gain back roughly 16 out of 20 megawatts. So it's a very, it was a very big gain for their facility and allowed the gas turbine to operate at its maximum capacity. Now, outside of the HRSG, there's different types of equipment, balance of plant items that can be affected by the upgrades. I'm not going to go into complete detail on all of these, but I just wanted to highlight some of these for you. Non-pressure parts are one that are oftentimes overlooked. So this is your liner systems, baffles, tube restraints. If they're not designed for the operating temperature, either in the inlet duct or downstream of the firing duct, you could have high temperature oxidation, thermal expansion, and constraint issues that could cause these non-pressure parts to fail. And this can also lead to pressure part issues downstream, saying that the tubes are not constrained as they were initially designed. Some of the balance of plant items that we typically see issues are the boiler feed pump capacity for the IP and the HP systems, low pressure feed water heater recirculation pump and condensate pump issues. Typically what you see here is the post-upgrade conditions cause the pump to run out of their capacity, but it's possible that there could be a pressure-related issue where they're not able to meet the economizer inlet demand pressure. And then some of the other BOP is flow level control valves. It's possible that they could exceed their flowing demand. And then with the emission control system, CO and SCR catalysts, the higher temperature may not allow the SCR to function as designed, and the higher increased turbine exhaust gas flow rate decreases the residence time for the catalysts to be effective. So a couple ways that you can prepare your facility for a gas turbine upgrade is to have a thermal modeling analysis performed prior to the upgrade being installed. This models all of the heating surfaces section by section, so you can look at each individual tube row. Using the gas turbine post-upgrade data, this will allow you to predict how the HRSG is going to operate, and the results are going to help you understand what the changes are in the HRSG performance, what your capacity and limitations are for the HRSG or the balance of plant, and also select operating limits and boundaries to help protect the HRSG. So the thermal modeling can be used to for upgrading equipment and design modifications as well. Let's say you understand that you need new pressure parts installed. This is one way that you can assess how those pressure parts are going to be, or if they're going to be designed to the correct standards. So in closing, the gas turbine upgrades are being pushed heavily, and they're definitely important in today's market for improving flexibility and being competitive. But it's important to understand that the HRSG and the balance of plant could have limitations before implementing the upgrade. So it's important to look at these ahead of time. And there may be certain operating points with your gas turbine upgrade that are just not practical to operate at. This could be due to HRSG or balance of plant system limitations. So thermal analysis is one way that you can assess the gas turbine upgrade to maximize the potential. And doing this ahead of time can help you select the correct gas turbine upgrade or understand what limitations you need to set prior to installing. I think I've used up all of my time, so if there are any questions.
Yeah, Evan, yeah, thank you. Yeah, you went just a little bit over, so if it's okay with you and you're going to stay till the end, we'll take a couple of questions at the end of the session. Is that okay with you?
Absolutely, that works for me.
Okay, thanks. Because Kirk had to disappear, so we'll come back to you at the end. There's a couple of questions here. So the next and final presentation today is by Bob, and please introduce yourself, Bob, and the topic.
Yep. Well, I'm Bob. Still Bob. Hang on a second. Well, if I could make this little thing go away, I would. All right. Can you see the screen?
No, not yet.
Oh, you can't, huh? Well,
Share button, Bob. There
yeah,
we go.
I did. There we go. Thank
There we
you.
go.
All right. One more moment. Barry, I'm going to start my timer this time. So, you can,
I've got your time.
yeah, well, I want to have it too, so I don't have you yelling at me.
Okay.
Okay. Anyway, all right. Listen, I'm gonna share a little more information with you about a subject we've talked about before, and that's erosion damage in the HP bypass pressure control valve. This has become pretty common over the last several years and continues. And now it doesn't want to advance. Okay, well. There we go. So this erosion is caused by water or wet steam passing through the pressure control valve. And when it does that, it damages the seat and plug and the seating surfaces. Once that valve starts leaking, you're now leaking hot steam into the downstream pipe, which is generally made of carbon steel. So as that leak rate increases, you eventually reach a point where the downstream temperature exceeds around 780 to 800 degrees Fahrenheit, and it will then damage the carbon steel pipe. Once the leakage progresses and approaches that kind of temperature, you must open the PCV to its minimum operating position so that the spray water valve and the superheater can come on and cool that downstream pipe. I want to get this in here early before we get lost in details. If you find yourself with that pressure control valve leaking such that you're overheating the downstream pipe or approaching it, do not manually open the attemperator spray valve in an attempt to cool down that pipe. If you do, you can guarantee you will cause cracking in the pipe, damage to the thermal liner, much more damage than you're going to otherwise have. So your only safe option is to put the bypass in service at its minimum steam flow position, and with the superheater and automatic, it'll come into service at whatever spray level it needs to be at, and you'll be in a safe condition. You're going to have a bit of a capacity and heat rate hit, but you won't damage equipment. So here's some couple of pictures of some of the damage. The one on the right, when they pulled it out, they said, "Oh, looks like my valve melted," but it didn't melt. That's just how severe the erosion was. This problem is not specific to any valve manufacturer. They all have suffered it and continue to suffer it. There have been some attempts to solve this problem with changing materials and changing design details. Those have not been completely successful. Some of the design work has helped it some and can slow the erosion, but I'm not aware of a design change that has eliminated it and made the valve capable of ingesting water without damage. Sometimes this occurs after only a few startups. The valve on the right, for example, it got in that condition after 2 or 3 starts, 2 or 3 operations of the bypass. Others, it'll run for many starts, and then the leakage begins. So where does this water come from? One source that the root cause assessments have identified in some units is, as we all know, when you start the unit, a considerable amount of condensate forms in the HP superheater. If you don't drain that water out completely before you open the bypass valve, that water is going to be sucked up and it's going to pass through the bypass valve. During hot layup, if you're using the bypass to reduce pressure for forced cooling, eventually the superheater outlet temperature gets down to saturation because you're not putting any heat in the boiler, and you start pulling water through the bypass. And we'll look at some data that shows those things here in a little while. Interstage attemperators and final stage attemperators are notorious for leaking. You know, as we've probably mentioned before, Barry and I have done many surveys of plants, and when I look at the thermal transients in the plant, I very often find leaking attemperators, spray valves, block valves, control valves. So that's a very common problem that's very important to fix. But if your attemperator is leaking, that's another way to put interstage attemperator. The water will accumulate in the superheater or the reheater, and when the bypass valve's open, it's sucked through. The final attemperator leaks, it's got a direct path through the main steam pipe to the bypass valve. I've seen some cases where there are permanent distortions in the steam pipes that create a low point that is not possible to drain it. So water accumulated in those undrained low points will be swept into the bypass valve if they occur upstream. The thing those things are pretty straightforward, and if you got them, you need to find them and fix them. The thing I want to talk about now is condensate formed in this steam pipe while you're warming that pipe work. You know, when you're starting a unit, and well, anytime you're warming a pipe, it forms condensate in order to warm the pipe. So let's look at the flow path for some startups here. So this is sort of simplified. We've got the superheater outlet over here. The HP pipe runs along here. Here's our branch T up to the HP bypass and on to cold reheat. Then we generally will come around a couple of bends, maybe change elevation. We're going to have a superheater outlet temperature measured here. You may or may not have a temperature measurement on the HP pipe downstream of this branch T. You're generally going to have a drain pot here with a temperature element in it, maybe, and a small bore drain valve. On a 2x1, 3x1 unit, you're going to have an isolation valve before you reach this common steam header going over here to our steam turbine. You'll have some temperature measurement on this common main steam pipe somewhere along the way, and you'll generally have a couple of warming drains very close to and at a low point under the steam turbine. So this is fairly common. Now on a lead start, which means it's the first gas turbine HRSG to start, steam turbine is shut down. You'll generally do that with this isolation valve open, these warming drains open. This drain is generally an automatic, so depending on what it may be an automatic or manual, depending on your procedures. These are generally always open, right? So the boiler's fire, the gas turbine's firing, the boiler's warming up. Steam, it starts steaming, making a little pressure. The flow path is down these pipes to these turbine drains here, and this whole pipe gets warmed up. Whatever condensate gets formed is swept along, comes out this drain or these drains or other drains. The bypass in this case is remaining closed. Here's some data from that type of cold start here. This is saturation temperature. The blue line is the superheater outlet coming out of the HP superheater. The green line is a temperature that is somewhere downstream of the bypass branch T. And depending on the unit, it may be a very long distance away or it might be closer. Somewhere in between those two is what's going to be going on at the bypass valve. So what happens to us here is the gas turbine lights off here, and being a cold start, about 30, 35 minutes later, the bypass valve opens. It's the red line here. When that occurs, the steam pipe temperature at the superheater outlet and the one downstream of the bypass branch T have heated because the steam is flowing to the warm-up drains at the steam turbine. They've heated up to 103 degrees C above saturation. This is a very good condition. When that bypass valve opens, it's getting plenty of superheat and dry steam. So this is not going to cause a problem. We make the same type of startup lead hot start. We've got the valve arrangement the same. When we start out on this hot start, the superheater outlet is already very hot. I apologize; these are in Fahrenheit here, but we're around a little over 900 degrees Fahrenheit at the superheater outlet. The steam piping further downstream, beyond the bypass, is still around 700 degrees Fahrenheit. So when the gas turbine starts, these pipe temperatures have decayed, but they're still well above saturation. So there's no need to warm them, and there's no condensate forming. So about 15 minutes after the gas turbine lights off, the bypass opens. These temperatures have already begun to increase, which is what you'd like to occur before you open the bypass. And we've still got plenty of margin, 82 degrees C margin to saturation. Again, there's going to be no water. This is what you'd like to see. Now let's talk about the lag startup, which is the second or third gas turbine to start. Now the valve arrangement there is different. You can see, because it's red, the common main steam header is already hot and flowing steam to the steam turbine that's operating. So before this isolation valve is closed when we start up this gas turbine in HRSG. So we begin to build some pressure, and the only flow path we have is this small bore drain right in front of this isolation valve. And I can tell you where this single 3 or 4 centimeter drain pipe is not going to move very much steam like these two 5 centimeter pipes did down here. So we don't have a good flow path established. Even if this thing is in manual and open, if it's in automatic, it's only going to intermittently open to discharge condensate that falls into the pot. It won't actually move any steam through the pipe. So inevitably, if that's the case, when we open this valve, then we begin to move steam through this way, and it's cold and wet. And here's some data showing that case. So the gas turbine fires, both the superheater outlet pipe and the main steam pipe further downstream from the bypass. They're tracking saturation temperature, which means if they are flowing steam, it's wet steam. The superheater outlet starts to warm, but again, remember that could be 40, 50, 60 feet upstream of the bypass valve, but the temperature downstream of the bypass valve is still at saturation till the bypass valve opens here. And so this is going to be wet steam that's pulled through the bypass valve. Now, once the bypass valve opens, we now have a robust steam flow to warm the pipes, and they warm right up. But it's too late now because we've already passed some water through the bypass. So this is from a more recent plant that I did an RCA for this on, and it happened to have a thermocouple at the inlet of the bypass valve. That's the only plant I've ever seen that on. Normally, you're having to use guesswork from this thermocouple and this thermocouple of what's going on in between them, or you might even have this one and only this one, but it's rare to have this one. So let's look at the data that came from that. This is a cold lag start. Okay, so this isolation valve is closed. This drain valve is in manual and open, so it's flowing all it can flow. But as we can see in the data, it's not, the gas turbine started way back here, right? So it's not doing a very good job of warming this piping. This green line is the drain pipe temperature. It's subcooled, so that tells us it's flowing water. The other problem with this startup is that the bypass valve opens, when it opens here, things start warming up, but like before, it's too late. The superheater outlet is subcooled and starts warming, so it's going to be pulling water along, and the downstream temperature is also below. So this is another case of water passing through, and it demonstrates that this valve is just not, this pipe is just not large enough to move enough steam to warm this deadheaded section of pipe, of HP pipe. So some simple stuff. Ensure that your HP superheater is drained during startup before you initiate steam flow. You want to do that for the superheater's benefit as well, but it's equally important to the bypass valve. You want to make sure your temperators don't leak. That's for the benefit of the temperator steam piping and the bypass. You'll need to review some DCS data looking at these upstream and downstream thermocouples on your HP steam pipe to determine when you have superheat and when it is safe to open the bypass. That in some cases, it may require you adding some additional thermocouples to look at pipe temperature locations that aren't in your normal instrumentation. Now, if you add thermocouples like that, I'm not suggesting you add a thermal well into the pipe. I'm suggesting that you spot weld just thermocouple wire, much like the post-oil heat treat people do, onto the outside surface of the pipe. And that will give you sufficient information to understand what's going on with the pipe, with the time dynamics that we're dealing with there. And finally, you want to avoid operation of the HP bypass during layup. And here I'll show you why you want to do that. So again, the blue line is superheater outlet temperature here. The gas turbine is shut down here. This is gas turbine speed, is the gray line. Okay, so it's shut down, and now it's high-speed cranking right along through here. This is black line saturation temperature again. So notice that and the bypass valve, red line, the bypass valve is cracked open and bleeding off steam because we're trying to depressurize the boiler more rapidly than it will depressurize cooling slowly. But the bypass valve is good for that, in that you can precisely control the pressure ramp rate and not come down with the pressure too fast so that you don't damage the HP drum. So these guys are trying to do the right thing, but they notice that the HP superheater outlet temperature drops to saturation fairly quickly. Now from this point on, we're making condensate in the HP superheater, and we're passing it through this bypass. So we are just chewing that valve up through this whole period. Now, I don't have the data here, but I will tell you this behavior is somewhat unit specific. Some units have enough residual heat in the gas path that this steam temperature doesn't come down so rapidly, and it'll take longer for it to reach saturation. Other units, if you don't immediately start this depressurization, but you wait a couple of hours and then you start it out here, the saturation temperature has decayed to the point that you may not reach saturation during this event. But you have to look at this kind of data in order to determine if how your unit's doing it. There's been some attempts that have been successful in some cases to solve this problem, and that's to start the unit with the bypass fully open. So that's what I've drawn here. Bypass is 100% open. This is a cold start. We can get away with that on a cold start because there's no pressure in the boiler to pass through the bypass until we generate some. So again, it's a lead start. Our isolation valve is open. Our flow path is as it was before, down to the turbine and through the bypass. But by the time with all this open, a startup like this did not cause wet steam to go through the bypass. So it's I suspect that has some bearing on the pipe configuration and those kind of details and where drains are. So I'm not suggesting this will always work in every case, and it may or may not work in your plant. But if you are having erosion problems with the bypass, you may be able to improve things somewhat by sneaking up on can you make a cold start with the bypass open and do less damage. You cannot do this on a hot start. If you've got pressure in the boiler, you cannot open this bypass to a large opening just because you want it to be open. You'll overpressurize your reheater and cause all kinds of other problems. So this will only work for a cold start. I think a solution, there are hundreds of 2x1, 3x1, 4x1 plants in the world that have this piping arrangement where you've got only a small drain in front of the isolation valve to the common header, and you have no means of establishing enough of a flow path to warm this deadheaded pipe without opening the bypass valve. So I'm suggesting here that plants that have this arrangement and are having erosion problems with the HP bypass, your solution may be to install a larger drain at this location so that you can get something like the steam flow to warm this section of pipe that is produced when you're doing it with these drains down here in the lead start. So that's my pitch with 2.5 minutes to spare, Barry.
Yes, that's very good. That's very good, Bob. And let me see. I don't think there was any questions came in for you. So let's wait until we do the other questions. And
Yeah.
What I'd like to do right now, though, is go to the sponsors. We want to support our good sponsors, so we'll have those, and then there's a few questions for Evan, and hope there might be some for you. So Chris Wellard from SWAN
Yes.
Analytical, are you there?
Yeah, I'm here. Hello.
Good. Yes, go ahead.
All right. Thank you very much. I'll just share my screen with you all. So make it larger for you. There we go. Okay. So thank you, first of all, to the steering committee for allowing us to do this short presentation. Much appreciated. I was actually trying to figure out how long SWAN has actually been with the ABHUG committee, and it's longer than what I can remember. So we really enjoy doing these conferences. A lot of people know about SWAN Analytical. They know that we do a lot of instrumentation, so I'm not going to go on to what parameters we do, but what I thought I'll do is for SWAN Australia and New Zealand is to show you guys what's new and what has been our successes over the last 2 years. Okay, so this is pretty much during COVID. So what's new at SWAN? So back in 2020, SWAN Analytical in Switzerland acquired another company called Ceres. Ceres is an instrument company based out of France. The reason behind this is to increase our parameters and our markets. So the main market of increase is the petroleum market. So we now have instrumentation for oil and water, some ATEX applications, but then also we've increased our parameters for the municipal, the wastewater, pharmaceutical, and also the boiler. Yes, we have another silica analyzer available and another TOC and a chloride analyzer for that market. New for New Zealand and Australia, we now have new staff that have joined us in the last 6 months. They're helping us with the sales support and service. So Karan Prescott, Keith Proctor, and Lewis Bander have all joined our team. So in due time, I'm sure you will all get to meet one or all of these new staff that we have. For SWAN Australia and SWAN Systems, SWAN Systems is our SWAS manufacturers in Switzerland. We've done some projects during the COVID-19 pandemic, and SWAN have been able to provide and support these large projects for the HRSG, coal-fired, and also the waste energy applications. So to date, we have successfully delivered and commissioned 9 boilers, SWAS wet racks, containerized or standalone, and it's equivalent to 2.82 gigawatts of potential generation that our instrumentations are supporting, which is really comforting because Marty McFly only needed 1.21 gigawatts for his flux capacitor, so we can send him back to the future twice. Further on that, we've also delivered, but yet to be installed in 2022, 6 more boilers in Australia. So as you can see, we've been quite successful in the combined SWAS wet rack installations for power generation. One of our latest projects, we have a 4-minute video. If Scott, if you can bring that on for me, please. This is one of the installations we had from start to finish. Customer was very happy with this project, obviously, and is still running today. It might have some sound on it, but we'll start. There we go. Thank you for showing that, Scott. If I can have the presentation back, there we are. Yeah, so as you can see, pretty much from steam coming in to signal going out, we've successfully installed a complete new system with a laboratory and so forth. The keys to the success is having the primary steam conditioning on the outside, being external. Reason for this is that there is no superheated steam coming into the container, which was found on the previous one. The previous container did have 2 exit doors, but there was one area at one side where if there was a steam leak inside the container, the chemist was basically cooked. So all safety aside, we took all those into account and made sure that the sample coming in did not exceed 65 degrees. With the secondary conditioning on the inside, we can guarantee 25 degrees C for all the instrumentation on a closed loop. Everything was ergonomic, safety equipment, safety chemistry equipment, fire extinguishers, so forth. It was all included. And the customized building met all the local building requirements. The increase of instrumentation to meet the standards, and also the communications Modbus plus 4 to 20 milliamp outputs were part of that as well. So that gives you a bit of an idea of the successes that we've had over the last 18 months during COVID. It's been pretty challenging, but it's been very fortunate to have done this, these projects. I must note that I've been wrapped on the knuckles because I forgot Jason Gray, who is also part of the new SWAN team. He actually joins me. So Jason, if you're listening, I do apologise. I'm sorry. I'll buy you a beer later on.
Oh, good.
Okay. Thank you.
Yeah, thank you. Thank you, Chris. That was very interesting and different. And we have one other sponsor from Water Treatment Services, and Leonie Huff. If you're there, please go ahead.
Yeah, well, hi there. Thank you for the opportunity to speak today. Well, we're almost at the end of day 2, and you've probably had enough of hearing from people like me, so I'll make it snappy. Apologies for that. We are now dancing to a new tune, a new set of buzzwords. This was emphasised in a presentation yesterday. Stations are having to follow market demand, which they were not designed to do. When units are required to be offline, storage options include wet or dry layout, with the overriding consideration of how quickly you can respond to bring the unit back online. New strategies are required to get these units to work in a way they weren't designed to work, allowing you to stay competitive. For more than 20 years, we've been delivering unique solutions with a diverse range of services to all major coal-fired power stations, some 50% of the total megawatt capacity. Of particular note is the supply of super high quality chemicals as an essential component in boiler treatment. As you are aware, this can often be a sneaky source of impurity ingress if you get it wrong. Also, the specific skills in sampling and trace analysis of contaminants, including corrosion product monitoring to industry standard guidelines, is critical. Earlier this year, we were acquired by Mac Water. It was a strategic step, allowing us to expand our capabilities into DMIN and RO. As you know, lots of things happen at power stations. Experienced feet on the ground can make all the difference when it comes to ensuring a smooth operation, site-specific solutions, and identifying the source of those strange idiosyncrasies that emerge from time to time. I'm sure you may know what I'm talking about. We've helped some others address these types of challenges. Thank you.
Hello?
Yes,
You
hi.
started. Oh, you're there. Okay.
Yeah. So that is the end of my presentation.
Oh, okay. Leonie, thank you. That was very
Just
nice.
very brief. I did promise a brief one.
Yeah, no, it's okay. There's no need to. We wanted to make sure that all the sponsors have some time. So thank you to Water Treatment Services and thank you to SWAN Australia. And we'll just finish off here as we still have 90 something people as part of it. There's a couple of questions here for Evan, if Evan is still here. And the first one is from Yun Tian from Synergy. And if he is here, he and Scott can switch him on. He can ask the question.
Yeah, my questions are just wondering if any long-term effects have been considered after GT upgrade. These probably include HRSG thick components like drum due to higher temperature or higher temperature gradient, degree Celsius per hour, sort of these things. This could be the long-term effects rather than the short-term effects of the over temperature or dissipating things.
Yes, the short answer to that is yes, there are definite long-term considerations for the gas turbine upgrade, both at base load and for faster startup. For base load operation, one of the issues that we discussed was the high temperature operation of the pressure part components, and there are studies that can be done looking at remaining life assessment, looking at historical operation to determine how much of the component life has been used up, and then using the post-upgrade gas turbine conditions to identify what those temperatures are going to be and how that could decrease the total lifespan of the component. And then as far as temperature gradient, the faster startups definitely have more of an impact, particularly on thick-walled pressure vessels like the HP steam drum, and identifying what those ramp rates are, degrees C per minute, is something that should be addressed. And typically, different types of limits can be established to maintain that ramp rate in an acceptable level.
All right, thanks.
Evan, thank you. And there's a question from Mark Wyburn. Is Mark still with us?
Sorry, how you going?
Yeah, excellent, Mark. Hello. Go ahead.
Yeah, g'day, Evan. I'm just wondering if you're seeing companies taking into account when they do a business case for a GT upgrade, whether including the loss of asset life on your HRSG components. Are they aware of it and adequately covering that in their capital costs and not just looking at the glowing increase in megawatt output from the GT?
Unfortunately, I think there is some of that. Is particularly at maybe the management level. Oftentimes they're seeing the increased megawatt output and what the potential is for that additional revenue. And there is some some of the maintenance planning does go by the wayside. I think some plants are becoming more wary of this. I know some of our clients in the US are anticipating these increased maintenance costs and are doing the gas turbine upgrade studies well in advance so they can plan for those. But I don't have, like a good number to say that a gas turbine upgrade is going to increase maintenance costs by 2% or something like that. But it is definitely something that needs to be addressed by the plant, and pre-planning can help with that.
Good, thank you. Evan, that's good. There was no response. So I just wanted to make a comment here. For quite a number of years at the ABHUG and the ABHUG meetings, we've talked about oxides and temperatures of superheater and reheater tubes, and we call it OGI, oxide growth and exfoliation. And we're trying to take a little bit of a proactive approach, because in brief, that might be, don't wait until you see the situation that you showed with massive amounts of exfoliation on the outside. And we're trying to take the same approach that we took with the HP evaporators, in terms of removing those and looking at the internal deposits so that we can stop failures from taking place. And that's exactly what we want to do here for superheaters and reheaters. So you can use that OGI index, and there's a paper. I don't know whether you've seen it or aware of it. I know that Lester is, and your boss, because I've talked to them before. But you can characterize the oxide by taking a sample. So you would measure the oxide thickness from the outside, and if that's above a critical level, then you can remove the tube and determine the stage in life where that superheater or reheater is. And so we're building up a database. I want to encourage you and any of your clients to join that, so that we can blossom it out. But at the moment, there's a very comprehensive paper that I've shared with many people, and I can share with you. I'm sure Lester might already have it. Anyway, it's to try to take a little bit more proactive approach instead of waiting for this oxide to catch you up, because as you probably know, there's oxidation limits, and some of your temperatures there are very close to them. You have oxidation limit for T22 of 580 degrees C, and for T91 of 605, and they're very close. They're very close to that. And when you get the oxide growing very thick on the inside, every time the oxide grows by 25 microns, it increases the tube temperature by 2 degrees. And so there are things that you can do, that you don't need to wait until you get into a situation where that you showed. So that was excellent. I was very enthused by that. The more we point out that oxide is very important, I think we'll get more people taking samples. So thank you.
Absolutely.
Bob, I lost Bob here. I don't think I see any other comments or any. Scott, are there any hands raised? We can go back to one that was before. I think there may be one more question here from Ori Seltzer. If we could just do that quickly. Ori, are you still here with us? This is another one.
Yeah, thanks, Barry. Evan, this was for you, and I don't know, it was strange to me. I heard a colleague who supports machines in the 50 hertz area, Europe, and he was saying that there were upgrades being done to actually lower exhaust gas temperature and then reduce the amount of spray. I don't know if this was related to temperature matching, something like that. But I just was curious, because I've always seen the upgrades lead to higher temperatures, more spray, as you pointed out in your presentation. So I just wanted to ask about any possible operational scenarios that would lead to, less spray or no spray operation after that, and a lower exhaust gas temperature. Because it can impact the attemperator in terms of rangeability, requiring very low amount of water spray then, instead of the opposite, as you pointed out, of overspray.
Yeah, that's a very good question, and there is one instance where the gas turbine upgrade can actually produce lower temperatures and lower temperature spray flow rates, and in the UK, there's been quite a push. I think there might be 10 to 13 plants that have implemented the GE variable load path upgrade. And this upgrade's a little bit more in-depth and specific than what I what I covered in the presentation. This particular upgrade modulates the inlet guide vane angle to produce, and I think you can see my screen here, both a hot load path, which would be considered, like peak firing, but it can also produce this cold load path by opening the IGV at its maximum angle. This actually can allow the gas turbine to run up to roughly 60 to 75% load without exceeding a turbine exhaust gas temperature of 800 degrees Fahrenheit. And it definitely has some effects. So this is one example showing the difference between a temperator spray water capacities along the hot load path and then along the cold load path. And if you look at them side by side, the hot load path causes the HPA temperator to reach its capacity very, very rapidly, while the cold load path, you can see here the gas turbine load reaches 90% before any spray water flow is required. So if you can imagine some intermediate path going through here, you might have some higher degree of a temperator spray water flow rates reaching a capacity. However, if you are following this cold load path most of the way up to base load conditions, it's quite possible that you're going to see lower spray water flow rates than you would at typical operation.
Good.
Yeah.
Okay.
Are there other side effects or drawbacks, like environmental or anything emission based in that?
Yeah, there are. I have a presentation that I could share with you after the fact, where the difference between the hot and the cold load path changes where the heat absorption of the HRSG is primarily. The cold load path shifts a lot of heat absorption to the IP and the LP system, and that actually causes more issues with capacity and pressure in the IP and LP system, whereas it doesn't affect the HP system as much. The hot load path, you can kind of assume that's similar to like a gas turbine low load instance where it's low exhaust gas flow rates, but very high temperatures.
Good.
Thank you.
Okay.
I have your email. I'll reach out to you. Thank you.
Yeah. Ori, thank you. And thank you, Evan, for staying on. I apologize. We ran about 10 minutes over here, but I wanted to get all the presentations that were prepared and the questions. So I think we've reached the point where we've answered all the questions, or we've raised all the questions, and we'll just have to close out the day here, unless Bob or Scott wants to say anything else, and we'll meet at the same time, same place tomorrow. Is there anything else, Scott? Don't see anything else.
Not for me.
Okay. Well, thanks, everybody. Thanks for participating and listening. We'll see you all tomorrow. Thank you.
Good night.
Night. Good morning
you.
for me. Good morning. Very, very early morning for me. Good. That's good.
Cheers.
Bob, saw that.